Welcome once more to this quiet place, your corner of the evening where the lights are low and the questions are deep. If you are here, lying beneath the silent ceiling, or just letting the mind drift, know that we are entering one of the oldest, strangest, and most persistent queries humanity has ever posed, the question of our own improbable existence. Tonight's quiet journey explores a puzzle that lies not in the stars themselves, but in the numbers that govern them. Is the universe a mistake? It is a thought that sounds dramatic, almost rude to ask of the soaring galaxies and the perfect balance of an atom. Yet the question is born from a place of genuine scientific wonder, a realization that the conditions for our existence are so delicately balanced, so fine-tuned, that they appear to defy all odds. The very moment we learned to count the cosmos, we realized we might not be entitled to be here at all. This thought begins softly, not with explosions, but with a few simple numerical constants, the fixed values of nature that define how the universe operates. Think of them as the settings on a grand cosmic dial. There is the mass of the electron, the charge of the proton, the strength of the force holding atoms together, which we call the strong nuclear force, the precise speed of light, and, of course, the strength of gravity itself. If you were building a universe from scratch, you would have to choose these numbers. And what scientists have discovered over the last century is that if you change any single one of them by a tiny, almost imperceptible fraction, the entire system collapses into sterile silence. Imagine, for instance, the strong nuclear force, the most powerful force we know, responsible for binding protons and neutrons into atomic nuclei. It is perfectly tuned to allow carbon to form, that essential element for all life as we know it. If the strong force were just 1% stronger, all hydrogen would have been instantly converted into helium in the early universe, leaving no hydrogen to form water or long-lasting stars like our sun. The cosmos would be a dark, short-lived ocean of gas. Conversely, if that force were just 1% weaker, no complex elements heavier than hydrogen could form at all. The universe would be stuck forever with the simplest atoms, a bland and utterly lifeless expanse of gas and dust. In either case, a tiny adjustment to the knob, and there is no carbon, no complexity, and no one to ask the question. Consider, too, the mass of the electron compared to the mass of the proton. Their ratio must fall within a narrow band. If the electron were much heavier, atoms would not be able to form stable, complex molecular structures, meaning no chemistry, no DNA, and no biology. If it were much lighter, the forces holding molecular bonds together would be too weak. Again, a slight tilt of the cosmic scale leads directly to the impossibility of life. The most famous of these tightrope walks involves the cosmological constant, often referred to as dark energy, which dictates the rate at which the universe expands. According to Einstein's original equations, this constant could, in theory, be any value. But if it were even slightly larger than the absurdly small value we observe, the universe would have expanded so rapidly in its first fraction of a second that matter would have dispersed instantly. Galaxies, stars, and planets would never have coalesced. The cosmos would be an almost perfectly uniform, rapidly thinning soup of particles, never cooling enough for anything interesting to happen. The maximum possible value for this constant based on quantum theory is estimated to be 1 followed by 120 zeros times greater than the observed value. This difference, a factor of 120 orders of magnitude, is considered by many physicists to be the single most mind-boggling mismatch between theory and observation in all of science. It is why the question of a mistake, or rather, an improbable lucky accident, arises. These are not isolated coincidences. They pile up one upon the other, creating what is known as the fine-tuning problem. The gravitational constant, the speed of light, the initial density fluctuations that seeded galaxy formation, each required a precision that seems wildly unlikely to have occurred by chance. The argument goes, if you had a 10-digit combination lock and all 10 numbers had to be correct to within one decimal point to open the door, and that lock opened on your very first random attempt, you wouldn't call it luck. You would suspect the lock was rigged or the choice was predetermined. The universe, in its own way, is a lock that opened on the first try. This leads to a quiet crisis of perspective. On one hand, we have the elegant beauty of our physical laws, which work perfectly to describe everything from the fall of an apple to the collision of black holes. On the other, we have a set of fundamental parameters that seem arbitrarily selected from a vast, sterile possibility space, yet which are absolutely essential for the formation of stars, chemistry, and conscious observers. Why should the universe permit us to be here? Philosophically, there are three classic responses to the fine-tuning problem, and we will drift softly through each of them, like leaf boats on a river of thought. The first response is the one that gives rise to the question of a mistake itself, pure, inexplicable chance. This is the hypothesis that the universe is exactly what it is, not because of design or a deeper law, but because we got incredibly, impossibly lucky. We rolled the dice a single time, and the dice came up with the winning combination. The reason we observe the life-permitting numbers is simply that if the numbers were any different, we wouldn't be here to observe them. This is the weak anthropic principle. The universe must have the properties it does, because if it didn't, observers, which is us, could not exist. The problem with this answer is that while it is logically true, it feels unsatisfying. It explains why we observe the balance, but doesn't explain the cause of the balance itself. It doesn't tell us why the initial probability of non-existence was so high. It leaves the universe feeling like a statistical fluke, a beautiful temporary error in the cosmic ledger. The second response involves the idea of a multiverse and natural selection. This shifts the statistical burden by suggesting that our universe is not the only universe. If there are not just one, but an infinite number of universes, a multiverse, each with slightly different fundamental constants, then the problem of improbable chance vanishes entirely. In an infinite possibility space, every combination of constants, including the one that permits life, must exist somewhere. Our universe is simply the one where the dice happen to land on the habitable configuration, and we, as the resulting observers, naturally find ourselves in that rare life-friendly corner. This turns the problem of physics into a problem of biology. The universe we inhabit is the one that was selected for by the simple requirement of life's existence. It is cosmic Darwinism. This idea is popular among physicists because it maintains the idea that the fundamental constants are truly random or variable, without resorting to the idea of a designer. It is elegant, but it raises a profound problem. The multiverse itself is, for now, beyond all empirical observation. It is a brilliant mathematical solution that cannot yet be tested, asking us to accept a potentially infinite, unobservable reality simply to explain the one we can see. The third response is to seek a deeper law or theory of everything. This perspective holds that the fine-tuning is an illusion. It argues that the fundamental constants we currently view as independent dial settings are in fact interlinked and constrained by an unknown underlying law. This future theory of everything, perhaps a final, unified version of quantum gravity, would show that the constants could not have been any other value. They are fixed, not random, and the universe had no choice but to be precisely the way it is. If true, the apparent fine-tuning is simply a sign of our incomplete understanding. We are looking at a complex equation with variables that appear independent, but which are all derived from a single final value. This is the most hopeful and most demanding path, requiring generations of physicists to search for the hidden connections and constraints that must exist if the universe is truly unique and governed by absolute logic. It removes the randomness and the multiplicity, returning to the ancient idea of a singular, perfect cosmos. Tonight, as we settle into the quiet, let the full weight of the question rest upon you. If the universe is a singular event, then the conditions for our life are a statistical miracle, a slip of the cosmic pen that somehow wrote existence where nothing was most likely. If it is one of many, then we are merely the residents of a quiet, lucky corner in an infinite, noisy sprawl. And if it is governed by a deeper, unyielding law, then we are not lucky at all, but merely the logical, inevitable product of an inescapable cosmic arithmetic. In all cases, the question itself forces us to confront the boundary between physics and philosophy, demanding an answer that is either breathtakingly simple or terrifyingly vast. Let us begin to turn the dials one by one, tracing the fine lines of this cosmic paradox, and see which way the numbers lead. The universe is patient, and the night is long, allowing the quiet truth of our fragile, improbable existence to softly unfold. Let us begin our gentle descent into the numbers, focusing first on the vast canvas of the cosmos itself, the forces that shape galaxies, and the initial conditions that set the stage for matter. If the question, is the universe a mistake, has a mathematical origin, it is found in the exquisite balance of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. These four interactions govern every event in the cosmos, from the tiniest flicker of a neutrino to the majestic spiral of the Andromeda Galaxy. And yet their relative strengths are wildly different, and their ratios are essential to our existence. Consider the ratio of the strength of gravity to that of electromagnetism. Gravity, the familiar, gentle hand that keeps our feet on the ground and planets in orbit, is the weakest force of all. It is so weak that the electromagnetic force holding the molecules in your fingertip together is vastly stronger than the gravitational pull of the entire Earth on your hand. In fact, if you tried to quantify this ratio, the strength of gravity compared to the strength of electromagnetism, you would find a number so small it defies easy comprehension, roughly 1 part in 10 to the power of 40. A tiny number indeed, 40 zeros after the decimal point before you get to the first significant digit. Why is this ratio so critical? If gravity were only slightly stronger, perhaps just 1 part in 10 to the power of 35, instead of 1 part in 10 to the power of 40, stars would burn out in a fraction of their current lifespan. They would form, collapse under their own enormous, quickened weight, and explode before they could generate the heavier elements essential for planets and life. A star like our Sun, which has sustained a stable environment for billions of years, would have lasted only a few million years. There would not have been enough time for the slow, meandering process of evolution to produce a conscious observer. The universe would be a rapid, fiery flash of activity, ending in darkness before complex life could begin. Conversely, if gravity were a little weaker, say 1 part in 10 to the power of 45, stars would be so diffuse and cool that they might never ignite at all, or they would be so spread out that planetary systems could not coalesce. The raw material would be there, but the engine of stellar fusion, the power plant of the universe, would not be able to generate the heat and pressure necessary to fuse hydrogen into helium, and eventually to forge the crucial atoms of carbon and oxygen. The cosmos would be a dark, dilute, and chemically simple place, with no light, no heat, and no complexity. The mere existence of a star that shines steadily for 10 billion years, like our own, is proof of this fine balance. A consequence of that number, 1 part in 10 to the power of 40, precisely calibrated to sustain long-term stellar fusion and permit the leisurely pace of biological evolution. Next, let us turn to the weak nuclear force, the mysterious interaction responsible for radioactive decay and, crucially, for the neutrino emission that regulates a star's core temperature. Inside a star, the fusion of hydrogen into helium produces a shower of subatomic particles, including neutrinos, mediated by the weak force. If this force were too weak, the star's heat would be trapped inside, causing an explosive meltdown and preventing the stable, steady burn required for life. If it were too strong, the fusion process would be too efficient, again causing stars to burn through their fuel too quickly and collapse prematurely. The stability of stellar burn, that dependable, life-giving light and heat we see every day, is a tribute to the weak nuclear force's perfect middle ground setting. But the most breathtaking tightrope walk of all occurs in the formation of carbon. Carbon is the backbone of organic chemistry, the element that allows for long, complex molecular chains, which makes DNA and all proteins possible. It is forged inside aging stars through a process called the triple alpha process, where 3 helium nuclei are fused together. For this process to work efficiently enough to create the vast amounts of carbon required for life, a specific ephemeral energy state, or resonance, must exist within the carbon nucleus. Sir Fred Hoyle, a brilliant and often controversial astrophysicist, predicted this resonance in the 1950s, arguing that the existence of life demanded its presence. He reasoned that if the universe was to produce carbon in abundance, there had to be an energy level in the carbon nucleus that exactly matched the combined energy of the 3 helium nuclei. If the resonance level were even slightly off, by just a few percent, carbon production would be almost impossible, and the universe would be devoid of organic life. Subsequent experiments confirmed Hoyle's prediction, finding the carbon resonance exactly where it needed to be. This required the strong nuclear force to be precisely tuned to allow the excited state of carbon to exist for the brief moment required to capture the 3rd helium nucleus. A slight adjustment to the strong nuclear force's strength, and the carbon bottleneck slams shut. Hoyle himself, an atheist, found this discovery deeply unsettling. He is famously quoted as saying that the facts suggest that a super intellect has monkeyed with physics, as well as with chemistry and biology. While Hoyle later explored alternatives, his sentiment, the overwhelming sense of a delicate, intentional setup, remains the emotional core of the fine-tuning argument. The universe seems geared for us, an elaborate, multi-stage machine where every gear is perfectly cut for the operation of the next. This cosmic precision is further complicated by the universe's initial conditions, specifically the amount of matter it contained and its uniformity. When the universe was barely a tiny fraction of a second old, it underwent a rapid burst of expansion known as inflation. This period was necessary to smooth out the early cosmos and explain why the universe looks so uniform in every direction. However, the initial density fluctuations, the tiny irregularities that would later collapse to form all the structure, all the galaxies and stars, had to be just right. If the initial fluctuations were slightly larger, the early universe would have immediately collapsed into black holes, never forming stars or galaxies. If they were slightly smaller, the gravitational clumping would have been too weak, and the universe would have remained a smooth, featureless gas. The universe's eventual structure, the clusters of galaxies, the stars, the planets, hangs on the delicate balance of these initial quantum jitters. The amount of matter itself, known by the Greek letter omega, had to be extraordinarily close to the critical density in the earliest moments. The deviation from this critical density in the early universe, scientists calculate, could have been no more than 1 part in 10 to the power of 60. The universe began not with a violent random burst, but with a highly controlled, incredibly precise setting of its own density and expansion rate. All of this cumulative evidence, the gravitational constant, the weak nuclear force, the carbon resonance, the initial density, forces the quiet scientist to ask, what are the odds? If these values were truly random, selected from a broad, continuous range of possibilities. The chance of all of them aligning to permit life is mathematically indistinguishable from zero. It is the universe as a hole-in-one on a billion-mile golf course. And so, we return to our three quiet paths of thought. The sheer improbability demands we abandon the idea of a single arbitrary roll of the dice. We are left with a choice. Either our physical laws are not arbitrary at all, but are mathematically fixed by a deeper law, or we are observers in a very lucky, very small fraction of an infinite multiverse. The fine-tuning paradox is, at its heart, a profound declaration of inadequacy. Our current physics is unable to explain our own existence. It compels us to search for the final, elegant theory that makes all the parameters inevitable, or the cosmic framework that makes our universe one of many. The current state of the cosmos, stable, chemically complex, and teeming with long-lived stars, is a challenge written in the most precise numbers. It is a whisper of the universe's quiet, astonishing arithmetic, and it demands to know if we are the logical conclusion of its laws, or merely the most spectacular error of its creation. The answer remains hidden, not in the stars themselves, but in the mathematical language that governs them. Our exploration of the universe's improbable existence leads us now to confront the most profound paradox of the fine-tuning problem: the role of the observer. We cannot discuss the universe's fine balance without acknowledging the unique, fragile piece of complexity that is asking the question, ourselves. The question, is the universe a mistake, is implicitly answered by our ability to ask it. This takes us into the quiet, sometimes contested territory of the anthropic principle. The anthropic principle is not a law of physics, but a constraint on physical laws. It states, in its most basic form, that the laws of physics must be such that they allow for the existence of conscious observers at some point in time. It is a tautology. If we are here, the universe must be compatible with our presence. But within this simple truth lie two distinct, deeply philosophical interpretations that change the way we view the fine-tuning. The first, the weak anthropic principle, is the mildest and most accepted form. It states that the observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there are places where carbon-based life can evolve, and by the requirement that the universe is old enough for that life to have appeared. In essence, this weak anthropic principle says, we should not be surprised to find ourselves in a life-friendly universe, because if we weren't, we wouldn't be anywhere at all. It is a selection effect, like finding a polar bear only in the Arctic. The bear didn't choose the Arctic, but the Arctic selects for the bear. The fine-tuning is explained away as a statistical bias inherent in our act of observation. The probability of the universe being life-friendly is still astronomically small, but since we are the measuring instrument, we can only ever measure the outcome that resulted in us. The weak anthropic principle thus addresses the who and where, but not the why. It is the universe as a silent, inexplicable miracle. The fine-tuning of the constants, gravity's strength, the carbon resonance, the cosmological constant, all become, under the weak anthropic principle, merely the prerequisites for a local observation. The vast, sterile region of parameter space, where life is impossible, still exists. We just happen to occupy the infinitesimal island of habitability. This perspective leaves many deeply unsatisfied. To say, it's just luck and we are the lucky ones, feels like an abdication of scientific duty, halting the search for a deeper explanation. It makes the universe seem almost accidental, a beautiful, temporary blunder in the cosmic ledger. This dissatisfaction leads naturally to the second interpretation, the strong anthropic principle. This version is far more controversial and suggests a kind of inevitability. The strong anthropic principle states that the universe must have those properties which allow life to develop within it at some stage. This moves the argument from a mere selection effect to a statement about the fundamental nature of the laws themselves. It implies that the fine-tuning is not an accident, but a necessity. The laws of physics are set up precisely because the universe is intended or required to produce observers. This word, required, is what makes the strong anthropic principle feel more like philosophy than physics, as it hints at either a teleological, goal-oriented universe or an unproven constraint that is simply outside our current physics. The strong anthropic principle suggests that the fine-tuning paradox is not a puzzle to be solved with more math, but a clue to a deeper law where the fundamental constants are not freely choosable parameters at all, but are mathematically constrained to be life-permitting. The universe isn't a mistake that produced us. It's a cosmic equation whose solution is us. The anthropic principle's greatest utility is its ability to predict the properties of unobservable reality, particularly in the context of the multiverse. The idea of the multiverse is, for many, the cleanest scientific escape from the fine-tuning paradox. If the weak anthropic principle is true, and if there are infinite universes, a landscape or ensemble of universes where the fundamental constants are randomized, then the existence of our own life-friendly corner becomes a statistical certainty. In this model, the multiverse is vast, unobservable, and inherently chaotic. It is the repository of all possible physical laws. Our universe, with its perfectly balanced constants and long-lived stars, is simply the single winning ticket among an infinite, continuous lottery. We do not need a designer or a deeper law. We only need to accept the existence of a grand ensemble. The fine-tuning of the cosmological constant, that problem of 120 orders of magnitude, is not a miracle in the multiverse. It's an expected outcome, observed only because any other outcome would have no one to observe it. This shift in perspective is enormous. It moves the focus from why our universe is special to the question of how the multiverse generates its diversity. One popular mechanism is cosmic inflation, the period of super-rapid expansion in the early universe. In some models, such as eternal inflation, the process of inflation doesn't stop everywhere at once. It continues indefinitely in most regions, bubbling off new pocket universes where the energy field that drives inflation settles down to different values, leading to different fundamental constants and different numbers of dimensions. Our entire visible cosmos would be just one small bubble in this eternally churning foam of creation. Another approach is string theory's landscape. String theory, a major candidate for a theory of everything, suggests that the universe has 10 or 11 dimensions. The fundamental constants we observe, like the strength of the electron's charge, are determined by how these extra dimensions are compactified, that is, how they are curled up. The geometry of this compactification is immensely complex, leading to an estimated 10 to the power of 500 different stable configurations, each corresponding to a unique set of physical laws and constants. This array of possible configurations is called the landscape. If a mechanism exists, perhaps eternal inflation, to realize all these possibilities, then we are back in the multiverse, where our fine-tuned constants are merely the result of sampling one very, very tiny corner of the landscape. The multiverse is an elegant, quiet solution to the fine-tuning. It neutralizes the problem by making it an environmental issue rather than a fundamental one. But it has profound consequences. If our universe is not unique, then its rules are not inevitable. They are random. The quest for a final, single perfect equation that governs all of reality, the ancient dream of the physicist, may be futile. There might be no deeper law, just a statistical distribution. We are left with a universe that is both magnificent and arbitrary, a beautifully written, life-permitting script that has no logical necessity behind it. However, the multiverse hypothesis faces a serious guardrail. It is, as of yet, untestable. How can we prove the existence of universes that, by definition, can never interact with our own? Critics argue that a theory that explains everything but predicts nothing is not science but metaphysics. If the only evidence for the multiverse is the existence of the fine-tuning problem itself, then the solution is merely an assumption brought in to ease our philosophical discomfort. In the quiet pursuit of truth, we must weigh this discomfort against the alternative, that the sheer, naked improbability of the fine-tuning in a single universe is the profound reality. The anthropic principle, whether weak or strong, guides our interpretation. It reminds us that we are not merely passive observers, we are the outcome, the living demonstration that the initial conditions of the cosmos were met with an almost unbelievable precision. The universe is not a mistake, but perhaps the one outcome in a near infinite array of failures that was structurally permitted to sustain the slow, quiet miracle of consciousness. The search now shifts from what the universe contains to what it permits. Having drifted through the statistical nightmare of fine-tuning and the conceptual sprawl of the multiverse, we now turn our attention to the final, most demanding path, the search for a deeper law. This is the ancient, quiet hope of physics, the belief that the universe is governed by a singular, logically perfect, and inescapable reality. If the universe is not a mistake, but the inevitable, unique consequence of its own internal logic, then the fine-tuning must be an illusion, a sign that we simply haven't discovered the right equation yet. This line of thought rejects both the inexplicable luck of the single universe model and the arbitrary randomness of the multiverse. It insists that the fundamental constants we currently treat as independent dial settings, the strength of gravity, the speed of light, the mass of the electron, are in fact linked and constrained. A future, final theory of everything would reveal a master equation from which all these constants are derived, showing that they could not have been any other value. If this is true, the universe had no choice but to be life-permitting. We are not lucky, we are mathematically necessary. The best hope for this deeper law currently lies in the quest to unify general relativity and quantum mechanics, a monumental task that has eluded the brightest minds for over a century. General relativity describes the very large, gravity as the geometry of space-time. Quantum mechanics describes the very small, particles and forces mediated by energy packets. The constants that define gravity's strength and those that define the electron's mass live in two separate, non-communicating mathematical languages. A unified theory would, by its nature, reveal the origin of these constants. In a truly unified field theory, the fundamental forces would not be separate entities. They would be different manifestations of a single underlying symmetry. The fine-tuning might then be explained not by arbitrary choices, but by the required stability of the theory itself. For example, the mathematical framework might only be consistent if the gravitational constant has its precise value relative to the strong nuclear force. The vast weakness of gravity, 1 part in 10 to the power of 40, is not a random number, but a mandatory ratio emerging from the geometry of the unified field. One key area of current research is exploring whether the constants are truly constant over cosmic time. If we could prove that the fine-tuned values have changed, even slightly, over the billions of years since the Big Bang, it would shatter the foundations of the current paradox. Experiments looking at the absorption spectra of light from distant quasars have provided some of the most stringent tests. These spectral lines depend on the values of constants like the fine structure constant, which governs the strength of electromagnetic interaction. If this constant were different billions of years ago, the wavelengths of light absorbed by ancient gas clouds would be shifted accordingly. So far, the tests show that the fine structure constant is constant, or nearly so, over the observable life of the universe. This lack of variation only deepens the fine-tuning problem, suggesting the constants were set at the very beginning and have remained locked in place. However, a more radical idea suggests that the fine-tuning is explained by cosmological natural selection, a hypothesis proposed by physicist Lee Smolin. This model offers an elegant synthesis of the multiverse idea and the search for a deeper law, suggesting that the laws of physics themselves evolve. Smolin proposes that every time a black hole forms, it acts as a rebirth event, causing a new, infant universe to bounce out of the singularity. Each new universe inherits the laws and constants of its parent universe, but with a slight, random mutation. Under this model, universes that produce more black holes are more successful at reproduction. Since the formation of black holes requires efficient star formation, and star formation requires the production of carbon and the formation of stable, long-lived stars, the laws of physics that favour life are also the laws that favour the creation of black holes. Over vast eternal timescales, a natural selection process would favour universes whose constants are fine-tuned for stellar stability, complexity, and maximum black hole production. Our universe, being life-friendly, is merely a very successful reproductive branch in the larger cosmological family tree. It is a scientific explanation that bypasses both the notion of pure luck and the untestable infinite ensemble, grounding the fine-tuning in a testable evolutionary mechanism. The search for the deeper law also touches on the nature of space and time themselves. The problem of the cosmological constant, that gargantuan mismatch of 120 orders of magnitude, is fundamentally a problem of vacuum energy. Quantum field theory predicts that even empty space is teeming with virtual particles constantly flickering in and out of existence, contributing an enormous theoretical energy to the vacuum. This vacuum energy is what drives the cosmic expansion, what we call dark energy. If this predicted quantum energy were real, the cosmological constant would be huge, and the universe would have blown apart instantly. The fact that the universe exists means that the underlying physics must somehow cause the total vacuum energy to cancel out with almost perfect precision, a cancellation of 1 part in 10 to the power of 120. Solving this problem is the holy grail of modern physics. It demands a theory where the zero-point energy of the vacuum is either forced to be exactly zero or is precisely compensated by an unknown field. This theoretical necessity, the required astonishing cancellation, is a huge signpost pointing toward the deeper law. It is the universe itself whispering that its current parameters are not random, but mandatory. If the universe is not a mistake, then it is a logical inevitability. The fine-tuning paradox, then, is not a flaw in the cosmos, but a flaw in our theoretical framework. It is a powerful, silent pressure, forcing us to search for the one elegant, unique mathematical truth that underlies all of reality. This deeper law, if found, would show that our existence is not a matter of luck, but a matter of arithmetic. It would restore the ancient serene vision of a universe that is singular, necessary, and logically perfect. Until that grand theory is unveiled, we live in a state of productive uncertainty, where the very act of asking, "Is the universe a mistake?" is the highest form of scientific prayer for the final, quiet answer. The quiet wonder of the cosmos compels us to look beyond the fine-tuning of the large-scale forces, gravity and electromagnetism, and to peer into the atomic heart of matter itself. Here, in the realm of the very small, where the dance of subatomic particles dictates the entire history of creation, the necessity of fine-tuning becomes even more acute, almost painfully precise. If the universe is not a mistake, it is because of an improbable series of subtle, exquisite, numerical adjustments deep within the standard model of particle physics. Let us focus on the particles that make up the atoms of your body and the air you breathe, the quarks and the leptons, which include the familiar electron. All of chemistry, all of biology, depends on the masses of these fundamental building blocks. Imagine the universe's design as choosing the weight settings on a microscopic scale. If the weights are wrong, the structure simply cannot stand. Consider the mass of the neutron versus the mass of the proton. These two particles are the fundamental components of the atomic nucleus. They are nearly identical in weight, but the neutron is slightly, fractionally heavier than the proton. This tiny difference is absolutely critical. If the neutron were even slightly lighter than the proton, all the protons in the universe would have decayed into neutrons in the first moments after the Big Bang. Since the neutron is electrically neutral, a universe made only of neutrons could not form atoms, which depend on the positive charge of the proton to bind with the negative charge of the electron. The cosmos would be a dark, dense soup of neutrons, incapable of supporting complex chemistry or life. The slight imbalance we observe, the proton is stable, the neutron decays, is dictated by the relative strengths of the weak nuclear force and electromagnetism, as well as the masses of the up and down quarks that compose them. The difference is only about 1 part in 700. It is this small, precise margin that allows hydrogen atoms, a single proton and electron, to exist stably for billions of years, providing the fuel for stars and the key component of water. The existence of every atom, every molecule, and every drop of water is predicated on this tiny numerical preference for the lighter proton. The balance is not merely close, it is the boundary between a sterile, featureless cosmos and one teeming with structured matter. This delicate balance extends to the electron mass. As we noted earlier, the electron must have its observed mass for stable atoms and molecules to form. If the electron were much heavier, quantum mechanics tells us that atomic orbitals, the quiet shells where electrons reside, would be significantly smaller. This compression would fundamentally change the properties of chemical bonds, likely making the complex, three-dimensional structures required for DNA and proteins physically impossible. If the electron were much lighter, the forces holding molecular bonds together would be too weak to sustain complex, stable structures at all. The entire edifice of chemistry, which depends on the predictable sharing and exchange of electrons, would collapse under the slightest pressure. The electron mass is thus the anchor for the entire chemical landscape, a number fine-tuned not for mere existence, but for the possibility of complex organized existence. And then there is the peculiar, quiet strength of the electromagnetic force. This force, governed by the fine structure constant, dictates how strongly charged particles interact. If this force were slightly stronger, it would make the fusion of hydrogen into helium in stars too efficient, causing them to burn out too quickly, as we have discussed. But it would also critically impact the structure of the atomic nucleus itself. If the electromagnetic repulsion between protons, which are positively charged and therefore naturally push apart, were stronger, it would overwhelm the strong nuclear force that is trying to hold them together. The vast majority of elements, all those heavier than hydrogen, would be unstable and immediately fly apart. We would have no oxygen, no nitrogen, and no calcium. The chemical universe would be reduced to a handful of fleeting, simple atoms. If the electromagnetic force was slightly weaker, fusion would be too slow and stars would be too cold and dim to sustain life. Moreover, it would allow atomic nuclei to become far too tightly bound, potentially creating stable, inert isotopes that would capture all the free neutrons, halting the production of many heavier elements. The universe's elemental diversity, that rich periodic table that allows for our complicated reality, exists within this narrow electromagnetic tolerance. The sum of these atomic fine-tunings, the proton-neutron mass difference, The electron's precise weight, the measured strength of electromagnetism, suggests a deep, hidden coherence. These numbers do not appear to be randomly chosen. They appear to be mutually required, interlocking parts of a single, functional machine designed for longevity and complexity. The puzzle becomes, how do these seemingly independent physical constants, masses determined by the Higgs field, forces governed by various coupling strengths, conspire to create a life-permitting reality? The deeper law perspective suggests that these numerical values are not independent at all, but are the logical outcome of a mathematical constraint. If, for instance, a future theory of everything shows that the Higgs mass, which determines particle weights, and the electromagnetic coupling, which determines atomic size, must be related by an exact, non-negotiable ratio, then the entire fine-tuning paradox dissolves. We are simply seeing the intricate, mandatory structure of reality. And our surprise is a reflection of our current ignorance, not the universe's improbability. Until that deeper law is found, however, the appearance is one of radical chance. The universe, in its quiet infancy, had to choose the weights of its fundamental components with an impossible precision, favouring a fragile imbalance, the proton lighter than the neutron, that allows for stable matter, and setting the speed and strength of its forces to permit the long, slow work of stellar evolution. It is a reality built on a razor's edge, a design so precise that if it were truly the result of random selection, we would have to call it the most extraordinary, beautiful mistake ever recorded. The narrative of cosmic fine-tuning finds its most dramatic and challenging expression in the concept of dark energy, which, as the cosmological constant, controls the ultimate fate and shape of the entire cosmos. If any constant suggests that the universe is an arbitrary fluke, a lucky roll of the dice, it is this mysterious, repulsive pressure that is driving the accelerated expansion of space. Imagine the universe not as a dense, hot fireball, but as a vast, quiet field of energy that permeates all of space, even the purest vacuum. This energy, known as vacuum energy or dark energy, acts as a kind of anti-gravity, pushing space apart. Einstein introduced a similar term, the cosmological constant, into his equations to force the universe to remain static, an idea he later called his greatest blunder after Edwin Hubble discovered the universe was expanding. Ironically, that concept, the cosmological constant, has made a dramatic return, now representing the dark energy that scientists observe today. The fine-tuning issue here is not subtle, it is catastrophic. According to the best theories of quantum mechanics, the energy of the vacuum, the quantum fluctuations constantly flickering into and out of existence, should contribute an enormous, almost incomprehensible density of energy to space. When physicists estimate this theoretical vacuum energy, the number is huge, a 1 followed by 120 zeros, in comparison to the value we actually measure. This is the infamous 120 orders of magnitude problem. If the theoretical vacuum energy were actually present in the cosmos, its repulsive anti-gravity effect would be so powerful that the universe would have expanded instantly and violently in its first fraction of a second. Space would have been torn apart before any matter could coalesce. Quarks could never have formed protons, atoms could never have formed molecules, and gravity could never have managed to pull together stars or galaxies. The cosmos would be a perfect, uniform, rapidly thinning soup of isolated particles, a reality so dilute and empty that nothing would ever happen. The universe we observe, however, has a cosmological constant so small it is almost negligible. The dark energy density we measure is incredibly, exquisitely tiny, enough to accelerate the expansion now, but not enough to have prevented the formation of stars and galaxies early on. This implies that the enormous vacuum energy predicted by quantum theory must be cancelled out by some other form of energy with almost flawless precision. The positive energy of the vacuum must be balanced by a negative energy field, with the two cancelling to 1 part in 10 to the power of 120, a cancellation of 1 followed by 120 zeros. This is a level of precision so absurd it is beyond intuition. To visualize it, imagine trying to aim a dart at a tiny target on the other side of the observable universe. The required accuracy is far greater than that. The fact that this near-perfect cancellation occurred is the single most powerful numerical evidence supporting the idea that our universe is either a statistical miracle or governed by a hidden constraint. If the cancellation were off by just a tiny bit, by 1 digit in the 120th decimal place, we would not be here. The multiverse hypothesis finds its strongest motivation in this problem. Since no known physics can explain this perfect cancellation, many physicists suggest that the cosmological constant is not fixed by a deeper law, but is simply a random variable that takes on all possible values across the multiverse. If there are infinite universes, and most of them instantly blow apart because of large vacuum energy, then we are simply residing in the one lucky bubble where the random value of the cosmological constant was small enough to allow structure to form. Our existence is proof of the tiny, habitable corner of the landscape. However, the dark energy problem also provides a strong imperative for the search for the deeper law. If the multiverse solution is rejected as unscientific, then the physics of the vacuum must be incomplete. A theory of quantum gravity that unifies general relativity and the standard model must, by necessity, include a mechanism that forces the total vacuum energy to be near zero. This mechanism might involve hidden symmetries or principles that we have not yet discovered. Supersymmetry, for example, a theoretical extension of the standard model, posits that every particle has a heavier partner, and these partner particles would contribute to the vacuum energy in a way that helps enforce the near-perfect cancellation. While supersymmetry has not yet been experimentally confirmed, its theoretical potential to solve the problem of 120 orders of magnitude makes it a compelling path for those who believe the universe is logically inevitable, not a mistake. The quiet truth is that the problem of dark energy forces us to question the deepest nature of nothingness. Is the vacuum truly empty, or is it a vibrant, seething quantum background whose fundamental properties are so delicately balanced that they permit the rest of the cosmos to unfold? Our continued existence, our ability to observe and measure this incredibly small cosmological constant, is the universe's most dramatic confession, a testament to a level of precision that defies our current understanding. Whether this precision is the result of blind astronomical luck or a mandatory, elegant truth waiting to be uncovered, the fate of the universe, its slow, gentle expansion into the future, hangs on the value of a number that, by all rights, should have been 120 orders of magnitude larger. The universe is not a mistake, but it is certainly playing a game of chance with stakes so high they are incomprehensible. Our journey into the fine-tuning paradox has thus far focused on the sheer improbability of the universe's numbers. But the question, is the universe a mistake, also contains a profound philosophical challenge. Does the nature of existence itself provide the answer? We must now quietly confront the possibility that the fine-tuning is an illusion created by the limitations of our own mathematical language. Imagine a reality so deep and complex that it can only be described by one perfect, unique, self-consistent equation. If that final equation exists, the theory of everything, it might dictate all the fundamental constants, from the speed of light to the mass of the electron, simply because the equation itself requires those values to hold. In this scenario, the universe is not the result of a random selection from a vast possibility space, but the inevitable, unique solution to the one possible cosmic arithmetic problem. The fine-tuning from this perspective is a symptom of incomplete physics. We currently treat about 25 different numerical parameters, the masses of all the fundamental particles, the strengths of the four forces, and the cosmological constant, as independent dials that could have been set arbitrarily. If we find that changing one dial requires the simultaneous change of another to maintain consistency, we haven't eliminated fine-tuning, but we have started to find the constraint that links them. The dream of the theory of everything is that all 25 dials are simply complex expressions of a single, non-negotiable master setting. Consider the hierarchy problem, one of the most persistent numerical mysteries in particle physics. This problem centers on the massive difference between the strength of gravity and the strength of the other fundamental forces, particularly the weak nuclear force. As we noted, gravity is incredibly weak, about 1 part in 10, to the power of 40 weaker than electromagnetism. This disparity creates a profound problem for theories that seek to unify the forces. In quantum physics, when we account for all the virtual particles constantly flickering in and out of the vacuum, the mass of the Higgs boson, the particle responsible for giving all other particles their mass, should be dragged up to an enormous gravitational scale. The fact that the Higgs boson is observed to be relatively light suggests an almost miraculous, precise cancellation of those quantum contributions. Without this near-perfect cancellation, the Higgs field, and consequently the masses of all fundamental particles, would be drastically different, likely rendering all chemistry and stability impossible. This necessary, exquisite cancellation is, in itself, a form of fine-tuning. Some physicists have argued that this immense numerical coincidence is too arbitrary to be natural, suggesting that the Standard Model is an unstable, incomplete structure. One popular theoretical resolution to the hierarchy problem is supersymmetry. This theory posits that for every known particle in the universe, there exists a heavier superpartner particle. These superpartners would exist in a way that allows their quantum effects to precisely cancel out the enormous contributions of the normal particles to the Higgs mass. If the theory is true, the massive fine-tuning of the Higgs is eliminated, replaced by fundamental, elegant symmetry. The universe is not a mistake, it is merely symmetrical in a way we have not yet observed. The search for this deeper law also changes how we think about the number of dimensions in the universe. We observe 4 space-time dimensions, 3 of space and 1 of time. But candidates for the theory of everything, particularly string theory, require 10 or 11 dimensions for the mathematics to remain consistent. If these extra dimensions exist, they must be curled up tightly, making them too small to detect in our everyday experience. The fine-tuning of the fundamental constants, then, might be dictated by the precise geometry of these hidden extra dimensions. The constants we measure, the strength of gravity, the mass of the electron, would be complex averages arising from the size and shape of these curled-up dimensions. If the size of one of these extra dimensions were slightly larger, the strength of the gravitational force might suddenly change, breaking the fine-tuned balance. The problem of fine-tuning moves from a numerical accident to a geometrical necessity. The universe is not fine-tuned by chance, but by the required self-consistency of its multidimensional geometry. However, even the quest for a deeper law faces a subtle, anthropic constraint. The law must be simple enough to be written down. Philosophically, a theory of everything that is so complex it could only be held in the mind of an omniscient being is unsatisfying. The most powerful, elegant physical laws, Newton's gravity, Einstein's relativity, are characterized by their stunning simplicity. The hope remains that the final theory will be so beautiful, so self-evident, that once seen, its inevitability will be undeniable. If the universe is not a mistake, then it is a work of art so singular that no other arrangement was mathematically permitted. The fine-tuning paradox, in this light, is a powerful prompt, a cosmic signpost urging us not to settle for mere statistical luck, but to continue the patient, quiet search for the single, elegant, inescapable truth that lies beneath all appearance. The universe is waiting for us to catch up to its own profound internal logic. Turning away from the equations and back toward the observable cosmos, we find the fine-tuning paradox reflected in the precise timing of the universe's life cycle, a cosmic calendar set with impossible precision. If the universe is not a mistake, it is because it achieved the perfect age to support life. The existence of any conscious observer, a creature capable of complex thought, built from heavy elements like carbon, oxygen, and iron, requires the universe to be billions of years old. This requirement creates a delicate constraint on the entire history of the cosmos, placing limits on its expansion rate, its initial density, and the lifespan of its stars. Life as we know it cannot form in the early universe, which was dominated by simple hydrogen and helium. These elements were created in the first few minutes after the Big Bang. To create the heavier, complex elements, the carbon backbone, the oxygen for water, the iron in your blood, stars must live and die. This is the stellar life cycle requirement. Stars are the universe's great foundries, fusing light elements into heavier ones in their cores and scattering those elements into space when they explode as supernovae. This process takes a long, slow time. Our Sun, a stable, medium-sized star, has a lifespan of approximately 10 billion years, about half of which has already passed. It took several generations of massive stars to live and die before enough carbon, oxygen, and other heavy elements were synthesized and collected into the nebula that eventually collapsed to form our solar system. The Earth itself, and therefore the life upon it, is composed of the ash of long-dead stars. The consequence is that the universe must be at least several billion years old to contain any complex observers. If the gravitational constant was slightly stronger, as we discussed, stars would burn out much faster, lasting only a few million years. The universe would be perpetually young, chemically simple, and sterile. If the cosmological constant were slightly larger, the universe would have expanded too quickly, preventing galaxies and stars from forming entirely. In either scenario, the cosmic clock runs too fast or too slow, missing the perfect window for complexity. The window for life is surprisingly narrow. It begins only after 2 or 3 generations of stars have lived and died, enriching the interstellar medium with carbon and iron. It ends, cosmologists predict, many tens of billions of years in the future, when the rate of star formation declines drastically, and the remaining low-mass stars, like our Sun, eventually exhaust their fuel and fade into dim, cold embers. The era we are currently in, the time between about 5 billion years and 15 billion years after the Big Bang, is often called the stelliferous era, the period where stable star systems and complex chemistry are most likely to exist. The fact that we are here now, precisely within this narrow temporary window of habitability, is another powerful fine-tuning constraint. If the universe were 100,000 times younger, it would be metal-poor and empty of complex life. If it were 100,000 times older, all the long-lived suns would have died out, leaving a cold, dark, and potentially empty cosmos. The timing of our existence is as finely tuned as the forces that govern the atom. Furthermore, the longevity of our own star, the Sun, is also dependent on the delicate physics of the weak nuclear force. This force controls the rate at which hydrogen is converted to helium in the Sun's core. If the weak force was slightly stronger, the fusion process would be too efficient, and the Sun would have burned out long ago. The steady, dependable light we rely on is evidence of the weak force's gentle, perfectly tuned restraint. The most unsettling aspect of this cosmic timing is that it points, again, to the anthropic principle. We find the universe to be old enough for us, because if it were not, we would not exist to note the time. But the strong anthropic principle would argue that the universe was required to run for billions of years, suggesting that a law must exist that enforces this necessary stellar longevity. The quiet, patient unfolding of the universe's history, the slow, steady rhythm of star formation, death, and element enrichment, is the ultimate context for the question, is the universe a mistake? If it were a mistake, it would have been a rapid, ephemeral flash, dissolving into the void before any complexity could take root. Instead, we see a process that is slow, dependable, and perfectly timed to deliver carbon, stable energy, and billions of years of peace, all the necessary conditions for the emergence of a creature capable of contemplating the cosmic clock itself. The universe, in its age, feels profoundly deliberate, not accidental. The most common escape from the fine-tuning paradox, the idea that the universe is a lucky mistake, is the notion of the multiverse. This hypothesis, favoured by many physicists, is a spectacular piece of philosophical engineering. It solves the problem of immense improbability by asserting that probability itself is not the right tool for the job. If our universe is just one outcome among an infinite ensemble, its perfect balance is no longer a miracle, but a necessity. We must now quietly drift through the conceptual landscape of this vast, unobservable reality. The multiverse is born directly out of our dissatisfaction with the weak anthropic principle. If we accept the idea that the constants of nature are random, we must confront the fact that the probability of them being life-permitting is vanishingly small. The multiverse simply shifts the question. Instead of asking why this universe is so special, it asks, what if there are enough universes that every possible combination of constants is realized somewhere? The theoretical framework for generating this ensemble often comes from cosmic inflation, the period of incredibly fast expansion that occurred in the first fraction of a second after the Big Bang. In the most speculative but mathematically compelling models, this inflationary process does not stop everywhere. Instead, it continues forever in most regions, acting as a perpetual engine of creation. This is known as eternal inflation. As the inflationary field decays in specific, localized regions, a new pocket universe is born, a bubble of space-time with its own Big Bang. Crucially, in some of these models, the random decay of the inflationary field leads to different physical parameters in each bubble. The strength of the four forces, the mass of the fundamental particles, and the value of the cosmological constant, all the dial settings we found to be exquisitely fine-tuned, are randomized across these infinite bubbles. Our entire observable cosmos, a vast expanse of billions of galaxies, would be just one small quiet pocket in this endlessly churning cosmic foam. Within this chaotic ensemble, the fine-tuning problem dissolves. If there are 10 to the power of 500 or even more universes, then it is mathematically guaranteed that one of them will have the perfect, improbable settings for carbon-based life to emerge. We, as conscious observers, naturally find ourselves in that one habitable pocket. Our life-friendly universe is simply the product of a selection effect, chosen by the necessity of our own existence. This is often connected to the string theory landscape. String theory suggests that the fundamental constants are determined by the geometry of its proposed 10 or 11 space-time dimensions. The ways these extra dimensions can be curled up or compactified are immense, perhaps 10 to the power of 500 possibilities, creating a landscape of possible physical laws. Eternal inflation then acts as the mechanism that randomly populates this landscape, creating universes that realize every one of those possible configurations. The multiverse, therefore, is the physical realization of the entire string theory landscape. The philosophical implication of the multiverse is profound. It removes the necessity for a deus ex machina, a predetermined design, or a deeper law that forces life to exist. The constants are arbitrary. The universe is not unique, and our presence is simply a consequence of colossal external chance. The universe is not a mistake, but it is not inevitable either. It is merely one successful accident among infinite failures. However, the multiverse faces a serious, quiet opposition, the problem of testability. Because these other universes are, by definition, outside our light cone and physically disconnected from us, we can never directly observe them. Critics argue that postulating an infinite, unobservable reality merely to explain a difficult feature of our own is not science, but metaphysical speculation. A theory that explains everything, but cannot be falsified by any observation, risks becoming scientifically sterile. Furthermore, the multiverse introduces a potential crisis known as the measure problem. If there are infinite universes, and observers exist in infinite copies with infinite variations, how do we assign probabilities to our observations? The answer depends on how you measure the infinity, how you define the probability distribution across the landscape, and no consensus has been reached. If we cannot assign probabilities, the very elegance of the multiverse, its ability to explain away the improbable, begins to unravel. Ultimately, the multiverse is an act of quiet, intellectual surrender to the idea of randomness. It is the assertion that the universe is not required to be elegant or logically inevitable. It simply has to be big enough and numerous enough to permit all possibilities. Our universe, with its perfect life-giving numbers, is the ultimate random draw. We are not the cosmic conclusion, but a statistical anomaly within an endless, chaotic sprawl. The feeling of surprise at our existence is simply an artifact of being lucky. The fine-tuning of the cosmos is not just apparent in the static constants of nature, but in the dynamic processes of creation itself. The question of whether the universe is a mistake is profoundly linked to the perfect, improbable balance between matter and antimatter in the earliest moments of existence. If this subtle imbalance had not occurred with extraordinary precision, the universe would be a dark, empty ocean of light, incapable of forming a single star or atom. In the first fraction of a second after the Big Bang, the universe was incredibly hot and dense, a state of perfect energy where particles and antiparticles were created and destroyed in continuous pairs. For every particle of matter, an equivalent particle of antimatter, with the same mass but opposite charge, was created. When they met, they annihilated each other instantly in a brilliant flash of energy. A universe that was perfectly symmetrical would have reached a point where all matter and all antimatter annihilated, leaving behind only a cold, vast sea of photons, or light particles. The existence of stars, planets, and ourselves is proof that a tiny, fractional imbalance occurred. For every billion pairs of matter and antimatter particles created, there was one extra particle of matter left over. This is the matter-antimatter asymmetry, a profound, life-giving bias in the fundamental laws of nature. That tiny residual matter, 1 part in a billion, is what survived the annihilation epoch and eventually condensed over billions of years to form all the galaxies, stars and planets we observe today. If this imbalance were off by a tiny minute fraction, if the excess of matter was 2 parts in a billion, or 0 parts in a billion, the resultant universe would be profoundly different. If there were no excess, the cosmos would be sterile light. If the excess were too great, the resultant universe would be too dense, leading to a much shorter, more violent history where stars and complexity could not exist. The puzzle is that the laws of physics, as we currently understand them, favour perfect symmetry. The standard model of particle physics incorporates mechanisms to break this symmetry, but they are not nearly powerful enough to explain the observed 1 part in a billion excess. This gap between the theoretical prediction and the observed asymmetry is one of the most significant unsolved problems in physics, often called the baryogenesis problem. The required mechanism for this imbalance must satisfy three conditions, first laid out by the Russian physicist Andrei Sakharov in the 1960s. First, there must be a process that violates baryon number conservation, meaning matter and antimatter are not preserved in equal numbers. Second, there must be a violation of charge and charge parity symmetry, meaning the laws of physics must behave differently when particles are replaced by antiparticles and their spatial coordinates are mirrored. Third, this process must occur when the universe is out of thermal equilibrium, meaning it is cooling rapidly, preventing the reversal of the process. The Standard Model does include the necessary violations of charge and charge parity symmetry, known as charge parity violation, but the effect is far too weak to account for the magnitude of the matter we see. This suggests that the universe's matter content is a direct consequence of physics beyond the Standard Model, new particles or forces that operated in the universe's earliest moments. The fine-tuning lies in the magnitude of this tiny bias. The laws of nature had to be written with a precise 1 in a billion preference for matter to allow structure to exist. If the universe were truly a mistake, one would expect perfect symmetry, leading to an empty, light-filled void. The presence of matter, the stability of the proton, and the complexity of the atomic nucleus are all direct consequences of this precise, non-accidental asymmetry. In the context of the multiverse, the matter-antimatter ratio could be yet another randomized parameter. Perhaps most pocket universes are sterile, light-filled voids, and we simply reside in one of the rare instances where a new particle or force emerged in the early moments with exactly the right properties to establish the 1 in a billion matter surplus. However, in the context of the deeper law, the baryogenesis problem is a profound hint. It suggests that the final unified theory must have a powerful, mandatory asymmetry built into its foundational principles. The origin of matter is not a random fluctuation, but a direct, inevitable consequence of the ultimate equation. The universe is not a mistake that produced us, but a precisely calculated deviation from symmetry that was required for structure to exist. The quiet, astonishing story of our existence is that every atom in your body is a survivor, the 1 in a billion remnant of an annihilation event that left behind a clean, elegant excess of matter. The cosmos, therefore, is not a mistake. It is the product of an improbable but perfectly executed asymmetry. The quiet discipline of cosmology dictates that we must extend the fine-tuning argument beyond the constants themselves and consider the structural stability of the universe's ultimate shape. The question, is the universe a mistake, can be rephrased. Could our universe have survived its own birth if its geometry was even slightly different? This brings us to the profound fine-tuning of the initial density parameter, often referred to by the Greek letter omega. The density parameter, omega, is the ratio of the actual matter-energy density of the universe to the critical density required to make the universe perfectly flat. In cosmology, flat does not mean two-dimensional. It means that on the largest scales, the geometry of space adheres to the rules of Euclidean geometry. Parallel lines remain parallel, and the angles of a large triangle add up to exactly 180 degrees. Einstein's general relativity tells us that the fate of the universe is tied directly to this number. If omega is greater than 1, the universe is closed like the surface of a sphere. The gravity of its own immense mass will eventually halt the expansion and cause everything to collapse back into a big crunch. If omega is less than 1, the universe is open, like the surface of a saddle. It lacks the gravitational pull to stop its expansion, and it will expand forever, becoming increasingly cold, dark, and empty. If omega is exactly equal to 1, the universe is perfectly flat, and the expansion will slow down to a halt only after infinite time. For a universe to be hospitable to life, it must remain in existence for many billions of years, allowing the long, slow processes of stellar evolution, element creation, and planetary formation to occur. A universe that quickly collapses or quickly dissipates into empty vacuum energy is incompatible with observers. The astonishing fine-tuning lies in the value of omega during the universe's earliest moments. To be approximately 1 today, the value observed by modern cosmology, omega had to be incredibly close to 1 at the time of the Big Bang, deviating by no more than 1 part in 10 to the power of 60. This is the flatness problem, and it is one of the most demanding numerical constraints on the universe's creation. If the initial density was slightly microscopically larger, say, off by 1 part in 10 to the power of 59, the universe's expansion would have halted within the first few seconds or minutes, collapsing before any structure could form. It would have been a quick, dramatic failure, a universe that died almost as soon as it was born. If the initial density was slightly smaller, the universe would have expanded so rapidly that gravity could never have overcome the expansion to pull matter into clumps. Galaxies, stars, and planets would never have formed. The cosmos would be an ultra-diffuse, featureless gas. The universe's ability to exist for 13.8 billion years, achieving the perfect age for complex chemistry, is a direct consequence of this almost unimaginable initial precision. The cosmos began on a razor's edge of geometrical stability, walking the tightrope between immediate collapse and immediate dispersal. The dominant explanation for this initial fine-tuning is cosmic inflation. This theory posits that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, doubling in size many tens of times over. This rapid, overwhelming expansion, driven by a hypothetical energy field, acts as a cosmic bulldozer. It stretches any pre-existing curvature or irregularity out of existence, effectively forcing the final geometry of the universe to be flat. In the context of the question, is the universe a mistake? The flatness problem offers 2 answers. If you accept the physics of cosmic inflation, then the initial fine-tuning of omega is no longer an arbitrary accident, but a mandatory outcome of the inflationary process. The universe is not lucky, it is the logical result of a specific type of rapid expansion. However, this only moves the fine-tuning problem 1 step back. Now we must ask, why was the energy field that drove inflation itself perfectly set to initiate and end inflation at the right moment, producing the observed tiny density fluctuations that seeded galaxy formation? The properties of the inflationary field, particularly its potential energy, must also be finely tuned. The flatness problem is thus a beautiful piece of cosmic arithmetic. It shows that the universe is not an arbitrary shape, but a highly specific structure required for longevity. It is a universe that had to choose perfect stability over chaos, and it chose that stability with a precision that defies explanation, without resorting to either an infinite ensemble of attempts or a single, inevitable master equation. The current flat geometry is a quiet testament to the fact that the universe had the foresight to survive its own violent birth. Our steady drift through the numerical paradoxes now requires us to examine a condition that seems purely environmental, yet is mathematically constrained: the necessity of 3 spatial dimensions. The universe we inhabit has length, width, and depth, in addition to the dimension of time. If the universe is not a mistake, it is because it chose the precise number of 3 dimensions of space, no more, no less, to allow for the possibility of stable structure and complex motion. Imagine a hypothetical universe with 2 spatial dimensions, like a vast, infinitely thin sheet. In such a universe, motion would be confined to the plane. The laws of gravity and electromagnetism, which diminish in strength with distance, would operate differently. The inverse square law of gravity which dictates that the force weakens with the square of the distance, is specific to 3 dimensions. In a 2-dimensional universe, gravity would diminish with the distance itself. The consequence for 2 dimensions would be catastrophic for life. Planetary orbits, which are stable ellipses in 3 dimensions, would be highly unstable. Planets would either spiral into their sun quickly or be flung out into the void. Stable, long-term orbits required to sustain life over billions of years would be impossible. Furthermore, in 2 dimensions, the complexities of biochemistry could not exist. Interconnected networks, such as those required for blood vessels or nervous systems, would divide the flat surface, preventing the free flow of necessary nutrients and information. A creature in 2 dimensions would essentially be cut in half by any internal loop or structure. Life would be reduced to extreme simplicity or would be impossible altogether. Now consider a universe with 4 or more spatial dimensions. Here, the fine-tuning problems are equally severe. Gravity would diminish much more quickly with distance, following an inverse cube or higher power law. This rapid fall-off of force would prevent stable, elliptical orbits, just as in the 2-dimensional case. Stars like our Sun would not be able to maintain stable fusion. They would quickly collapse into black holes, or their gravitational influence would be too short-range to bind a stable planetary system. Furthermore, in 4 or more dimensions, the behavior of atoms themselves is fundamentally altered. The principles of quantum mechanics that dictate the quiet stability of electron orbitals around the nucleus would fail. Electrons would not be confined to stable, predictable shells. They would tend to spiral into the nucleus. Without stable electron orbitals, stable atoms, the building blocks of all matter, could not exist. The entire foundation of chemistry, and therefore life, would disintegrate. The number of dimensions is thus a profound example of fine-tuning by structural consistency. It is not a random variable, but a necessary prerequisite for the observed laws of physics to yield the observed structure of reality. The choice of 3 spatial dimensions is the only one that allows for 1. The inverse square law of gravity to create long-term stable orbits. 2. The laws of quantum mechanics to create stable, complex atoms. And 3. The geometrical space for complex non-dividing biological networks. The problem for a deeper law is to explain why the universe chose 3 dimensions. String theory, as we noted, posits 10 or 11 dimensions, with the extra 7 or 8 dimensions being compactified or curled up into tiny spaces. If this is true, the universe did not choose 3. It simply exists in all 11, with the extra dimensions being too small to affect our large-scale physics. The stability of our 3 large dimensions is then determined by the precise geometry and size of the curled-up ones. The problem is simply transferred to the fine-tuning of the compactification process. In the context of the multiverse, the existence of 3 large dimensions is another randomized feature. Most universes might be sterile 2-dimensional sheets or 4-dimensional hypercollapsed voids, and we simply reside in the extremely rare bubble where the geometry unfolded into 3 stable spatial dimensions. The choice of 3 dimensions is a quiet, powerful constraint. It suggests that the universe is not a random system that happened to work, but a system that is inherently constrained by the requirements of its own internal consistency. The number 3 for space, alongside the 1 dimension of time, is a prerequisite for our very ability to think about the universe's numbers. The universe is not a mistake. It is a reality whose very structural integrity depends on a precise, non-negotiable count. Our ability to move, to stand, to form thoughts is a tribute to the quiet perfection of this spatial choice. The most compelling argument that the universe is not a mistake lies in the perfect balance of the nuclear forces that govern the creation of the elements essential for life. This is the quiet miracle of the carbon resonance, a story written in the heart of dying stars, and a constraint so specific it stunned the scientists who discovered it. To exist, any form of complex life requires heavy elements: carbon to form long molecular chains, oxygen to form water, and nitrogen to form proteins. These elements are forged in the intense, high-temperature environment of aging stars. The process of creation itself is a precarious cascade, where each step requires an exquisite numerical alignment. The challenge is to get past helium. The fusion of two hydrogen nuclei creates helium, but the next step, fusing helium into something heavier, is exceptionally difficult. Fusing two helium nuclei, known as alpha particles, results in a highly unstable atom, beryllium-8, which almost instantly decays back into two helium nuclei. It is a bottleneck in the cosmic factory. For life-supporting elements to be created, a third helium nucleus must collide and fuse with that fleeting beryllium-8 before it decays. This triple collision results in the formation of carbon-12. This process is statistically rare, but the universe found a way to make it efficient enough to fill the cosmos with the necessary carbon. The efficiency is achieved through a phenomenon called nuclear resonance. Resonance is essentially a matching energy level. For the triple alpha process to produce large amounts of carbon, the combined energy of the three helium nuclei must exactly match an excited energy state within the carbon-12 nucleus. Think of it as tuning a radio to catch a very weak signal. The frequency must be precisely correct. Sir Fred Hoyle, a pioneering astrophysicist, was one of the first to grasp the magnitude of this fine-tuning in the 1950s. He argued from the premise of our own existence. Knowing that carbon was essential for life, he predicted that the carbon nucleus must possess this specific, unknown resonance energy level. If it did not, there would be no carbon in the universe, and therefore no astronomers to observe it. Subsequent experiments confirmed Hoyle's stunning prediction, finding the carbon resonance exactly where it was needed to be to maximize the efficiency of carbon production. The numerical precision required for this resonance is breathtaking. The resonance energy must be set to within 4% of the combined energy of the three helium nuclei. If the strong nuclear force, which governs the binding energy of the carbon nucleus, were even slightly different, say 1 or 2% stronger or weaker, that energy level would shift, the resonance would be missed, and carbon production would cease almost entirely. The universe would be stuck perpetually in a helium age. Furthermore, this carbon resonance also had to avoid a catastrophic side effect: the rapid creation of oxygen. Oxygen is created when carbon-12 captures yet another helium nucleus. If the resonance for the formation of oxygen-16 were also too perfectly aligned, all the newly formed carbon would be instantly converted into oxygen, leaving nothing behind to build organic life. The constants of nature had to be tuned to make carbon production efficient, but oxygen production slightly inefficient. This numerical choice ensures a healthy cosmic ratio of both carbon and oxygen, the twin pillars of biochemistry. This required double fine-tuning: the perfect resonance for carbon and the imperfect resonance for oxygen is seen by many as the most striking evidence against the universe being a statistical mistake. The probability of two independent energy levels aligning with such precision is astronomically small if the nuclear forces were truly random. The fine-tuning of the carbon resonance suggests either a highly improbable accident, which the multiverse explains by sheer number, or an inescapable constraint, which the deeper law seeks to uncover. If a future unified theory shows that the strong nuclear force's strength is mathematically required to yield this specific resonance, the entire process moves from luck to necessity. The quiet truth is that your ability to think, the stability of the chair you might be sitting on, and the very air you breathe are all direct consequences of a near miraculous numerical setting deep within the laws of nuclear physics. The universe, in the act of element creation, seems to have had the foresight to choose the precise path to complexity. Our current understanding of the universe relies on a serene, logical order. The laws of physics are assumed to be invariant, meaning they hold true everywhere in space and at all times in history. But the fine-tuning paradox compels us to ask, are the constants of nature truly fixed, or is the universe potentially a mistake because its rules are not static? This leads us to the quiet, subtle search for variation in the fundamental constants. If the fine-tuning is simply a lucky draw from the cosmic lottery, then the constants should be arbitrary, fixed at the Big Bang and remaining unchanged. But if we could detect even a minuscule change in a fundamental constant over billions of years, it would suggest a new, deeper layer of physics, potentially resolving or compounding the fine-tuning problem. The most widely tested candidate for such variation is the fine structure constant, which governs the strength of the electromagnetic force, dictating everything from how atoms absorb and emit light to the size of the atomic nucleus. If this constant were slightly different in the distant past, the spectral lines of light absorbed by ancient gas clouds in distant galaxies would be shifted compared to the lines we measure in our terrestrial laboratories today. To search for this change, astronomers use the light from quasars, immensely bright, distant objects that emit light that has travelled across billions of light years. As this ancient light passes through intervening clouds of gas and dust, atoms in those clouds absorb specific wavelengths, leaving distinct spectral fingerprints on the light. By comparing the position of these fingerprints to laboratory standards, scientists can essentially measure the value of the fine structure constant billions of years ago. The results, collected over decades of painstaking observation, are complex but mostly point toward the constant being remarkably stable. If there is any variation, it is confined to a difference of mere parts per million across the entire observable history of the universe. This finding is profound. It confirms that the extreme fine-tuning required for life was not a temporary state, but a fixed, non-negotiable condition for nearly 14 billion years. The universe is not a chaotic system whose rules evolve. It is a monument to numerical rigidity. However, some controversial observations have suggested extremely slight spatial variations, hints that the fine structure constant might be different in one direction of the sky versus another. If confirmed, this would be a catastrophic finding for current physics, suggesting that the universe is not isotropic, or the same in all directions, at a fundamental level. A universe whose laws change, depending on which way you look, would imply a universe that is fundamentally random, and possibly an accidental failure of symmetry. The search for variation also extends to the proton-to-electron mass ratio. This ratio determines the size of the atomic nucleus relative to the electron's orbit, a critical factor for chemistry. Again, by observing ancient molecules in distant gas clouds, scientists have measured this ratio with exquisite precision over cosmic time, and found it to be virtually constant. The balance that keeps the proton stable and the electron in orbit has not wavered since the universe was young. The philosophical weight of this stability is enormous. If the constants had changed over time, the fine-tuning problem would be less acute. Life could be viewed as a temporary adaptation to a shifting reality. But the observed invariance of these constants forces us back to the original dilemma. The universe's parameters were set at an improbable, life-permitting value at the very beginning, and have remained locked there ever since. This numerical rigidity strengthens the case for the deeper law. If the constants were random, one might expect slight, continuous drifting over time. The fact that they are anchored so perfectly suggests that they are not arbitrary selections, but rather the required outputs of a stable, self-consistent equation. The quiet pursuit of these cosmic anchors, the fine structure constant, and the proton-to-electron mass ratio, is the physicist's way of testing the universe's sincerity. Is the universe a chaotic scribble whose rules are temporary? Or is it a single, profound statement whose meaning has not changed since the first moment of time? The current evidence suggests the latter. The universe is not a mistake. It is a text written in an unchanging, ancient language whose grammar demands its precise numerical settings. The quiet discipline of examining the universe for a flaw or a mistake must eventually turn to the most exotic and extreme objects in the cosmos: black holes. These regions of space-time, where gravity has overwhelmed all other forces, are the ultimate test of physical law, and their very existence is dependent on a delicate fine-tuning of the initial universe. If black holes were too numerous or too small, the universe would have dissolved into chaos. A black hole forms when a massive star collapses under its own gravity, concentrating its mass into a point of infinite density called a singularity. But the conditions for this to happen require a precise history of matter density and clustering. First, consider the efficiency of gravity itself. As we have discussed, gravity is incredibly weak, about 1 part in 10 to the power of 40 weaker than the electromagnetic force. This extreme weakness is the main reason why stars can live for billions of years without collapsing instantly. If gravity was slightly stronger, not only would stars burn out too quickly, but the universe's initial density fluctuations would have caused matter to collapse into countless small, primordial black holes almost immediately after the Big Bang. A universe dominated by these tiny, fast-forming black holes would have no time for stellar evolution, no creation of heavy elements, and no space for stable planetary systems. The cosmos would be a dark, dense, and sterile environment. The existence of our long-lived, middle-aged sun and the relatively small number of observed black holes is a testament to the quiet, subtle strength of gravity, just strong enough to form stars and galaxies, but weak enough to prevent the immediate, catastrophic collapse of all matter. Second, the stability of the proton is critical to the black hole paradox. According to the standard model of particle physics, the proton is assumed to be absolutely stable, meaning it does not decay. If the proton were to decay, all matter would eventually turn into light energy, eliminating the possibility of matter-based structures, including black holes and, of course, life. But if the proton is truly stable, then the immense concentrations of matter within a black hole's singularity remain stable. This long-term stability is required for black holes to play their crucial role in cosmic evolution, such as anchoring the centers of galaxies. However, many grand unified theories, which aim to link the strong, weak, and electromagnetic forces, predict that the proton must decay, albeit over an incredibly long timescale, far longer than the current age of the universe. The fact that the proton appears stable places strong limits on the parameters of these unifying theories, suggesting that any deeper law must be precisely tuned to delay proton decay for an almost infinite duration. This is another layer of fine-tuning. The laws of physics must be set to ensure that matter, the very fuel for black holes and life, does not decay, allowing the cosmic clock to run long enough for complexity. Third, supermassive black holes, those gargantuan objects at the centers of nearly all large galaxies, are essential for galactic stability and structure. They are not merely destructive, they regulate star formation and provide the gravitational anchor for billions of stars. Yet the initial formation of these objects is deeply mysterious, requiring a massive accumulation of gas and stars in the early universe. This efficient gathering of mass could only occur because the initial density fluctuations, the tiny ripples of matter distribution left over from the Big Bang, were set to a precise, small amplitude. If those fluctuations were too large, we get the collapse into small black holes everywhere. If they were too small, we get no large-scale structure, and therefore no supermassive black holes to anchor the galaxies. The black hole population is thus a direct measure of the universe's successful tightrope walk. We have just the right amount of gravity, just the right amount of initial density, and just the right long-term stability of matter to create black holes that are powerful enough to structure the cosmos, but not so numerous or fast-forming as to destroy it. In the context of the question, is the universe a mistake? The fine-tuning of black hole formation suggests that the cosmos is a highly optimized system. It is a system designed to maximize both stability and complexity, creating massive gravitational structures slowly and deliberately. If the universe were a mistake, it would have been a catastrophic failure of gravitational stability, collapsing or dispersing instantly. The existence and distribution of black holes, paradoxical as they are quiet evidence that the universe has mastered the art of long-term survival. The search for numerical proof that the universe is not a mistake extends beyond the physics of forces and into the essential chemistry of life itself. The emergence of water, the unique solvent that forms the basis of all known biology, is itself dependent on a striking fine-tuning of the electromagnetic force and the masses of the atoms involved. Water, a deceptively simple molecule composed of 2 hydrogen atoms and 1 oxygen atom, possesses properties that defy conventional expectation. It is often called the universal solvent because of its ability to dissolve more substances than any other liquid, a trait crucial for the complex chemical reactions required for life. This unique property is a consequence of its polarity. The oxygen atom pulls electrons closer to itself than the 2 hydrogen atoms, creating a slight negative charge near the oxygen and a slight positive charge near the hydrogens. This imbalance makes the water molecule act like a tiny magnet, capable of attracting and organizing other molecules. The existence and stability of this polarity, and therefore the existence of liquid water, is a direct result of the fine-tuned strength of the electromagnetic force and the precise mass of the electron. If the electromagnetic force was slightly weaker, the oxygen atom would not pull the electrons hard enough, and the water molecule would lose its polarity. It would be a non-polar solvent, incapable of supporting the complex, charged interactions required for biochemical reactions, such as the folding of proteins or the structure of DNA. Furthermore, water exhibits the unique, improbable property of being less dense as a solid than as a liquid. Ice floats. This feature, which is almost unheard of among common substances, is absolutely critical for life's survival on Earth. If ice were denser than water, it would sink to the bottom of oceans and lakes. In temperate and polar regions, this sinking ice would accumulate over time, eventually freezing the bodies of water solid from the bottom up, making sustained aquatic life impossible. The fact that ice floats creates an insulating layer on the surface of water bodies, protecting the liquid water below and allowing life to survive frigid conditions. The phenomenon of floating ice is a direct consequence of the unique way water molecules bond in a 3-dimensional lattice structure when they freeze, a structure only possible because of the precise angular shape of the water molecule, which in turn is dictated by quantum mechanical orbital properties. These quantum properties are tied directly to the masses of the atoms and the strength of the electromagnetic force. If the electron's mass were even slightly different, the angle of the water molecule might change, altering the lattice structure and potentially causing ice to sink. The second critical fine-tuning related to water is its high specific heat. Water can absorb a large amount of heat energy before its temperature rises. This property allows large bodies of water, like oceans, to act as enormous thermal buffers, stabilizing the temperature of planetary environments and preventing the wild, rapid temperature swings that would make life impossible. This high specific heat is again a result of the strong hydrogen bonds between water molecules, which are controlled by the strength of the electromagnetic force. The very chemistry of the cosmos, the way hydrogen bonds with oxygen, is a numerical masterpiece. The universe needed to choose a specific, precise strength for electromagnetism that ensures three improbable properties of water: that it is polar, that it has a high specific heat, and that its solid form floats. If any one of these properties were missing, the entire machinery of life would fail. The fine-tuning of water chemistry is a powerful argument for the non-mistaken nature of the universe. It suggests that the cosmos did not merely stumble upon life, it possessed foundational laws that actively enabled it. The laws of nature are not just random parameters. They seem to be a prerequisite toolkit for carbon-based complexity, written with a clear, if silent, mandate for organization. If the universe were a random mistake, the probability of finding this triple coincidence in the properties of water is negligible. Instead, we see an elegant interconnected web of physical necessity leading directly to the possibility of a world where life can thrive. The silent necessity of water is one of the universe's most persuasive arguments against its own accidental status. Our ongoing investigation into the quiet arithmetic of existence now brings us to a phenomenon so subtle that it was only hypothesized decades ago, yet it encapsulates the core fine-tuning problem: the role of neutrinos. These ghostly particles, which possess mass and travel at nearly the speed of light, are arguably the most numerous massive particles in the universe, passing through your body by the trillions every second without effect. Their existence, their precise mass, and their ability to oscillate are all critical components in the argument against the universe being a mistake. Neutrinos are fundamental particles, born in the intense, high-energy reactions within the sun supernovae and nuclear reactors. They come in three flavors, associated with their heavier siblings: electron, muon, and tau neutrinos. For decades, they were believed to be massless, but experiments confirmed in the 1990s that they possess a minuscule, non-zero mass. This discovery, that neutrinos have mass, was a revolutionary finding for particle physics, but it immediately introduced a new fine-tuning problem. The fine-tuning lies in the total sum of the neutrino masses. For the universe to exist in its current state, with structure and galaxies, the sum of the masses of the three neutrino flavors must be incredibly small, less than 1/millionth the mass of the electron. If the total neutrino mass were significantly larger, the universe would have been dramatically different in its early history. Neutrinos, being so numerous, act as a kind of gravitational drag. If they were heavier, they would have constituted a much larger fraction of the total matter content of the universe. This increased gravitational influence would have smoothed out the small density fluctuations that seeded the formation of galaxies and clusters. The universe would have remained largely uniform, and gravity would have been unable to pull matter together into the large-scale structures we see today. The cosmos would be a vast, mostly featureless expanse of gas, with few or no galaxies, a sterile outcome for a supposedly random system. The fact that we have galaxies, clusters, and a cosmic web of structure is direct evidence that the total mass of the neutrino is precisely limited to that small, narrow range. This is the neutrino mass problem in fine-tuning. A universe whose laws permit the existence of these particles, but only if they are almost massless, thus allowing gravity to win the structure-building race against the smoothing effect of massive neutrinos. Furthermore, the very mechanism by which neutrinos acquire mass is deeply mysterious, often pointing towards physics beyond the standard model. Their masses are vastly smaller than all other particles, suggesting a different, unknown process. One hypothesis is the seesaw mechanism, which posits the existence of incredibly heavy, sterile, right-handed neutrinos, whose quantum mechanical effects seesaw to push the mass of the ordinary left-handed neutrinos down to the observed minuscule levels. If the seesaw mechanism is true, the incredible lightness of the neutrino is not a random parameter, but the required inverse consequence of an equally incredible mass scale in some hidden sector of the universe. This moves the fine-tuning from the smallness of the mass to the gigantic mass of the hypothetical sterile neutrino, which then becomes part of the hierarchy problem we have discussed. The vast difference between the gravitational scale and the particle physics scale. The quiet, astonishing truth of the neutrino is that it is a ubiquitous survivor, a near massless ghost whose subtle presence had to be perfectly measured in the beginning of time. If the universe were a mistake, one would expect the masses of its fundamental particles to be distributed somewhat randomly, leading to a much heavier neutrino that would have suffocated cosmic structure. The incredibly light mass of the neutrino is a precise numerical choice that ensured the universe could form galaxies, allowing the long, slow work of complexity to proceed. The neutrino, therefore, is not just a particle. It is a quiet, powerful constraint. Its mass is the cosmic gatekeeper, set with immense precision to allow structure to form, providing profound evidence that the universe is a system optimized for complexity, not chaos. Our investigation now moves from the numerical to the philosophical, confronting the question of whether the universe is a mistake by examining the very nature of explanation itself. If the universe is a singularity, a unique self-contained reality, then the fine-tuning problem is not a problem of physics, but a problem of probability. The fine-tuning paradox is built on the premise that the constants of nature are random variables chosen from an enormous possibility space. For instance, the strength of the strong nuclear force could have been any value between 0 and 1, and we simply observed the one value that allows for carbon. Probability dictates that the chance of randomly selecting that one life-permitting value is negligible. However, probability, as a tool, is only valid when the event being measured is truly random and repeatable. The universe, by its very definition, is a unique, one-time event. We have no other universes to compare it to, and we have no experimental evidence that its constants could have been otherwise. The criticism of the fine-tuning paradox is that it misapplies the concept of probability to a non-random, non-repeatable event. Imagine finding a 5-leaf clover. If you assume all clovers have an equal chance of having 5 leaves, the probability is minuscule, making your finding a miracle. But if you then discover that the clover you found is genetically engineered to always produce 5 leaves, the probability calculation becomes meaningless. The event is not random, it is mandatory. The deeper law argument for the fine-tuning paradox suggests exactly this. The constants of nature are not random draws, but are the mandatory consequence of the universe's underlying unique equation. If the universe is the single, unique solution to the theory of everything, then the probability of it having life-permitting constants is 100%. The question, is the universe a mistake, is then exposed as a fallacy of logic based on a faulty assumption of randomness. This leads us to the concept of simplicity and elegance in physical law. Throughout the history of science, the most successful theories are the ones that are the most elegant and simple, reducing vast complexities to a few core principles. General relativity, which describes gravity as the curvature of space-time, is a classic example of this. The fine-tuning paradox, with its need for 25 seemingly independent, miraculously set constants, is the opposite of elegance. It suggests a kludge, a system jerry-rigged for a specific outcome. Proponents of the deeper law argue that the fine-tuning is an urgent call for simplification. The final theory must not merely explain the constants, but must reduce the number of independent parameters to a minimum, perhaps even to 1. The sheer numerical requirement for fine-tuning, the 10 to the power of 40 in gravity's weakness, the 1 part in 10 to the power of 60 in flatness is too ugly to be the final truth. It is a sign of an incomplete equation that requires external tuning. This philosophical push is what drives the search for grand unified theories, which aim to show that the strong, weak, and electromagnetic forces were all the same strength under the extreme energy conditions of the early universe. If successful, this reduces three seemingly independent forces to one, simplifying the number of arbitrary constants. The remaining differences we see today are then explained by predictable, known mechanisms as the universe cooled and the symmetries broke. The fine-tuning paradox is thus a quiet test of our philosophical confidence. Do we trust the apparent improbability and embrace the randomness of the multiverse, accepting that the universe is not unique? Or do we trust the historical track record of science, believing that the apparent ugliness of fine-tuning is a temporary veil that will be lifted by a single, beautiful, and inevitable truth? The question, is the universe a mistake, is therefore a profound tool of discovery. It forces us to choose between an infinite, arbitrary cosmos and a singular, mandatory one. The universe is not a mistake if its structure is required by an underlying principle of simplicity. It is merely waiting for the human mind to find the one, elegant explanation that reveals its necessity. The quiet integrity of the universe demands we consider the fine-tuning of its temperature history. If the universe is not a mistake, it is because its thermal evolution, from the fiery heat of the Big Bang to the cool darkness of the present, unfolded with a required, improbable precision. Any deviation in this cooling rate would have prevented the formation of atoms, chemistry, or complexity. The history of the cosmos is essentially a long, slow cooling process. In the first 380,000 years, the universe was an opaque plasma, a dense, superheated soup of charged nuclei and electrons. Light could not travel freely, trapped by the constant scattering off these charged particles. This period was fundamentally incompatible with life. No stable atoms or molecules could exist in such heat. The critical moment came at the recombination era, approximately 380,000 years after the Big Bang. At this point, the universe had expanded and cooled sufficiently to a temperature of roughly 3000 Kelvin to allow the free electrons to combine with the charged atomic nuclei, protons, and helium nuclei. This process created the first neutral, stable atoms of hydrogen and helium. The formation of these neutral atoms, called recombination, was the single most important thermal event for cosmic structure. Once atoms formed, the universe suddenly became transparent, allowing light to travel freely. This ancient light, redshifted by the expansion of space, is what we observe today as the cosmic microwave background, the faint, pervasive afterglow that fills all of space. The fine-tuning lies in the precise timing and duration of this era. If the expansion of the universe had been even slightly faster or slower, the cooling rate would have been altered, and recombination would have been fundamentally changed. If the cooling had been too rapid, the electrons and nuclei might have combined too quickly, leaving behind a universe with insufficient free charged particles to interact with the early structure. If the cooling had been too slow, the universe would have remained opaque for too long, delaying the formation of neutral matter and the subsequent gravitational collapse into stars and galaxies. The fact that recombination happened when it did, creating the stable hydrogen and helium atoms that are the fuel for all subsequent stellar processes, is a profound numerical constraint. It suggests that the initial density parameter and the cosmological constant, the parameters governing the expansion rate, were perfectly synchronized with the forces of electromagnetism, which dictates the energy required for electrons to bind to nuclei. Furthermore, the overall temperature of the cosmic microwave background today, roughly 2.7 degrees above absolute zero, is not arbitrary. This residual temperature is the memory of the Big Bang, stretched and cooled by billions of years of expansion. Cosmologists study the tiny faint temperature fluctuations within this background, variations of just a few parts in 100,000, because these fluctuations are the seeds of all subsequent structure. They represent the tiny, initial ripples of density that, thanks to the perfect thermal history, were able to grow into the vast galactic clusters we see today. If these initial temperature fluctuations had been slightly larger, the gravitational clumping would have been too aggressive, leading to the immediate formation of massive black holes and short-lived, unstable structures. If they had been slightly smaller, gravity would have been too weak to overcome the universe's expansion, resulting in a smooth, featureless cosmos without galaxies or stars. The amplitude of these initial fluctuations is thus another parameter that had to be exquisitely fine-tuned. The thermal history of the universe is a story of three critical numerical convergences: the perfect timing of recombination, the precise cooling rate that led to stable atoms, and the tiny, precise amplitude of the initial density ripples. These thermal constraints demonstrate that the universe is not a chaotic system. It is a highly controlled thermal engine that ran its course at the exact, mandatory speed required to transition from a sterile plasma to a structured, matter-dominated cosmos capable of supporting complexity. The universe is not a mistake, it is a successful thermal experiment. The most elusive fine-tuning argument, and perhaps the most humbling, centers on the Higgs field and the particle it excites, the Higgs boson. The properties of this field, which permeates all of space and gives mass to all fundamental particles, are constrained by a numerical precision that defies chance, strengthening the case that the universe is either a statistical anomaly or an inevitable design. The Higgs field is the mechanism by which particles acquire mass. Particles interact with the field, and the strength of that interaction determines their mass. Without the Higgs field, all fundamental particles would be massless and travel at the speed of light, unable to form atoms, chemistry, or complexity. The universe would be a featureless, light-speed blur. The existence of mass, and therefore the existence of matter, is a direct consequence of the quiet hum of the Higgs field. The key fine-tuning paradox here is the mass of the Higgs boson itself, which was discovered at the Large Hadron Collider in 2012. The observed mass is surprisingly light, about 125 giga-electron volts. This relatively low mass places the Higgs field firmly within the energy scale of the weak nuclear force, allowing it to interact effectively with the particles of the Standard Model. The fine-tuning problem, known as the hierarchy problem, arises when we try to connect this light Higgs mass to the much larger scale of gravity, the Planck scale, where gravity is expected to unify with the other forces, is vastly more energetic, about 1 part in 10 to the power of 17 times the energy scale of the weak force. In quantum theory, the mass of the Higgs boson should be enormously affected by quantum fluctuations in the vacuum, particularly those involving virtual particles. These fluctuations should drag up the Higgs mass toward the immense gravitational Planck scale. However, the fact that the Higgs boson is observed to be relatively light suggests that its theoretical mass contributions must be cancelled out with an almost impossible precision by other unknown quantum effects. This required cancellation is estimated to be 1 part in 10 to the power of 32. The universe requires this miraculous cancellation, because if the Higgs mass were dragged up to the gravitational Planck scale, its field would be too strong. The particles we know, the electron, the quarks, would become immensely heavy, preventing the formation of stable, large atoms and molecules. A heavy Higgs would lead to a universe that is either instantly collapsed or too dense for complexity. A light Higgs, like the one we observe, ensures that particles have the perfect, life-permitting mass, light enough to form atoms, but heavy enough to hold them together. This required cancellation is the single most powerful numerical argument for physics beyond the Standard Model. It suggests that the Standard Model, while successful, is an unstable house of cards that needs an external, unseen scaffolding to maintain its light Higgs mass. The most popular candidate for this scaffolding is supersymmetry, which posits that every particle has a heavier, compensating partner. These superpartners, if they exist with the right masses, would provide the quantum cancellation needed to keep the Higgs boson light, effectively solving the hierarchy problem and eliminating the fine-tuning. If supersymmetry is true, the apparent fine-tuning of the Higgs mass is not a mistake, but a symmetrical necessity. The universe is not lucky, it is merely symmetrical in a way we have not yet observed. The search for superpartners at particle accelerators is therefore a direct test of the fine-tuning argument itself. If superpartners are found, the fine-tuning is explained by a deeper, elegant law. If they are not found, the problem becomes even more acute, suggesting either a much more bizarre, unknown mechanism for the cancellation, or strengthening the argument for the multiverse. The Higgs field, therefore, is the quiet, invisible architect of the life-permitting universe. Its numerical properties are constrained by a precision that is either an incredible coincidence or a mandatory requirement of the final law. The question, is the universe a mistake and talk, in the context of the Higgs, is a direct challenge to the Standard Model, demanding a deeper explanation for the existence of mass and the delicate balance between the particle world and the gravitational world. The universe is not a mistake, it is a system that has mastered the art of quantum mechanical self-cancellation. The profound challenge posed by the question, is the universe a mistake, is that it touches on the philosophical debate regarding the nature of laws versus boundary conditions. In physics, a law is a general principle that governs the evolution of a system, such as Newton's law of motion. A boundary condition is a specific state of the system at a particular time or place, such as the initial position and velocity of a planet. The fine-tuning paradox blurs this distinction, suggesting that the laws themselves are boundary conditions for our existence. The fundamental constants, the strength of gravity, the speed of light, the particle masses, are generally regarded as laws because they define the rules of interaction for all time and space. Yet, because they had to be set to a miraculously precise value at the beginning of time, they act like initial conditions for the universe's ultimate outcome. Consider the initial low entropy of the universe. Entropy is a measure of disorder or the tendency of a system to move from order to chaos. The second law of thermodynamics dictates that the total entropy of a closed system can only increase. For the universe to exist in a state where complexity, structure, and life could emerge, it had to begin in a state of extremely low entropy, an incredibly ordered state. This ordered beginning allows for the long, slow process of stars burning and galaxies forming, which are local decreases in entropy powered by the vast overall increases in cosmic disorder. The initial low entropy of the universe is a powerful, inescapable boundary condition that is as finely tuned as any constant. If the initial entropy had been slightly higher, the universe would have started in a state of greater disorder, preventing the smooth, structured collapse of gas clouds into stars and galaxies. The cosmos would have rapidly moved toward a state of heat death or uniform distribution, unable to sustain complexity. The existence of gravity, which creates order out of chaos by pulling matter into dense clumps, is what allowed this low entropy state to transition into the structured cosmos we see. The fine-tuning of this initial low entropy is particularly unsettling because it is deeply related to the arrow of time. The reason time moves forward and not backward is the universe's continuous movement from its ordered, low entropy beginning to an expected, high entropy future. If the universe were truly a mistake, one would expect it to begin in a high-entropy, chaotic state, which is statistically far more probable. The incredibly low entropy beginning is a profound numerical choice that enforced the long predictable flow of time and the possibility of complex, time-dependent processes like life. This numerical constraint forces us to look at the three responses to the fine-tuning argument through the lens of initial conditions. If the universe is a singular event, its low entropy beginning is a colossal, unexplained piece of luck, a statistical fluke that defies the odds. If the low entropy is a feature of the multiverse, it suggests that most universes are born with high entropy and instantly die, and we are in the rare bubble that managed to start in an ordered state. However, if the low entropy is a mandatory consequence of a deeper law, then the ultimate unified theory must contain a principle that forces the universe to begin in an orderly state. This principle might be a feature of quantum gravity or the inflationary field, suggesting that the initial condition itself is dictated by the underlying laws, thus collapsing the distinction between law and boundary condition. The quiet complexity of our existence is therefore rooted not just in the fixed dials of nature, but in the improbable starting line. The universe did not merely choose the right rules for the game of life. It started the game at an exquisitely ordered moment, enabling the slow, elegant unfolding of cosmic history. The universe is not a mistake. It is a system that mastered the art of the perfect beginning. Our steady investigation of the universe's numerical constraints now requires us to consider the dark constituents of the cosmos, matter and energy we cannot see or touch, yet which determine the large-scale geometry and fate of everything. If the universe is not a mistake, it is because of a delicate, improbable balance between dark matter and dark energy. The universe we observe is dominated not by the familiar atoms of your body and the stars, which constitute only about 5% of the total mass-energy content. The remaining 95% is composed of mysterious, unseen entities, approximately 25% dark matter and 70% dark energy. The ratio between these two dark components is an additional, profound fine-tuning problem. Dark matter is the invisible gravitational scaffolding of the cosmos. We know it exists because its immense gravitational pull is required to explain the observed rotation speeds of galaxies and the clustering of galaxies into vast structures. Without dark matter, galaxies would simply fly apart. Its properties, it interacts gravitationally, but not electromagnetically, hence it is dark, had to be perfectly tuned. If dark matter particles were too light, they would move too fast and would not be able to clump together to form the necessary gravitational seeds for galaxies. If they were too heavy, they would have caused a premature, aggressive collapse of matter in the early universe, leading to a cosmos dominated by too many small black holes. The observed slow, majestic pace of galaxy formation confirms that dark matter particles fall within a precise, narrow mass and interaction range. Dark energy, as we have discussed, is the repulsive force, the cosmological constant, driving the accelerated expansion of the universe. The fine-tuning problem here is the vast numerical gulf of 120 orders of magnitude between the theoretically predicted vacuum energy and the observed minuscule dark energy density. The new layer of fine-tuning emerges from the ratio between dark matter and dark energy. For the universe to become habitable, it needed a long period of time to form structure, stars and galaxies, which requires the dominance of dark matter's attractive gravity. But it also needed to eventually accelerate its expansion, driven by dark energy, to avoid a gravitational collapse. The universe began with a high density of dark matter and ordinary matter, and a comparatively low density of dark energy. Because the density of dark matter dilutes as the universe expands, while the density of dark energy remains constant, as it is a property of space itself. There was a critical moment, only about 6 billion years ago, when dark energy began to dominate dark matter. The universe is life-permitting because this shift in dominance happened late in cosmic history. If dark energy had been slightly stronger, or if dark matter had been slightly less dense, dark energy would have dominated much earlier. In that case, the expansion would have accelerated aggressively before enough time had passed for galaxies and clusters to fully form and stabilize. The gravitational scaffolding of dark matter would have been overwhelmed, and the universe would be a mostly structureless void, unable to produce the star systems and planetary environments required for life. The delicate, quiet fact is that the universe waited for approximately 8 billion years, just enough time for 2 generations of stars to live and die, forming carbon, oxygen, and our sun, before dark energy began its aggressive takeover. This perfect timing of the cosmic transition is an extraordinary coincidence. In the context of the multiverse, this suggests that the relative initial settings of dark matter and dark energy densities are 2 more random variables that just happen to fall into the habitable zone, with the dark energy being delayed long enough for life to arise. In the context of the deeper law, the precise ratio and timing suggests a unified theory must exist that mathematically links the particle properties of dark matter, which determine its density, and the vacuum properties of dark energy, which determine its constant repulsion. The universe is not a mistake. It is a system governed by a slow, perfectly staged shift in its dominant components, designed to maximize the time available for complexity. The hidden majority of the cosmos, dark matter and dark energy, are tuned to ensure that the small, visible minority of stars and life could endure. The most compelling proof that the universe is not a mistake lies in the quiet, cumulative interconnectedness of the fine-tuned parameters. The paradox is not merely that one constant is perfectly set, but that many seemingly independent constants are all simultaneously set to values that favor life. This web of dependency strongly suggests that they are not random, but are constrained by a deeper, singular mechanism. Imagine for a moment the cosmic dials we have explored: the gravitational constant, the strong nuclear force, the cosmological constant, and the electron mass. If these were truly independent choices, the probability of them all landing in the life-permitting range is the product of their individual, tiny probabilities, a number so small it borders on absolute zero. Consider the double dependency of stars. A star like our sun requires fine-tuning at 2 entirely different energy scales. First, its long, stable lifespan is dictated by the weakness of gravity, a large-scale, low-energy parameter, and the strength of the weak nuclear force, a small-scale, high-energy parameter. Gravity must be weak enough to allow the star to burn slowly over billions of years, and the weak force must be precisely tuned to regulate the nuclear fusion in the core, preventing a runaway explosion or an immediate collapse. The simultaneous required settings of these 2 forces, operating at vastly different scales, are an extraordinary coincidence. Second, the life-giving product of the star, carbon, is constrained by the strong nuclear force, which sets the carbon resonance, and the electromagnetic force, which determines the size of the nucleus and the repulsion between protons. The strong force must be precisely strong enough to bind the nucleus, but the electromagnetic force must be weak enough that it does not entirely overwhelm the strong force, ensuring the stability of larger atoms. The required balance between these 2 forces is so tight that a slight change in either one causes the disintegration of the elements essential for biochemistry. The fine-tuning, therefore, is not a series of lucky draws. It is a nested hierarchy of constraints. The formation of galaxies constrains the initial density. The formation of stars constrains gravity and the weak force. The formation of atoms constrains the electromagnetic and strong forces. and the formation of carbon constrains two of the nuclear forces against each other. The system is structurally interdependent. This interconnectedness is the strongest argument against the multiverse hypothesis as a complete explanation. If the constants are truly random across the multiverse landscape, then we should be suspicious of why all the life-permitting constants correlate perfectly. For instance, if the strong force is randomly strong, the gravitational constant should be randomly weak. But for life to exist, the strength of the strong force must be related to the weakness of gravity by a complex, functional ratio. A truly random ensemble should produce universes with only one of the necessary life constants set correctly, leading to a sterile, non-functional cosmos. The fact that all the constraints are met simultaneously in our universe suggests a single, underlying physical mechanism that links them. This leads directly back to the necessity of a deeper law. The final unified theory must be a single framework, where the apparently independent constants are linked by a set of non-negotiable ratios. The existence of the life-permitting universe is simply proof that this ultimate mathematical reality is self-consistent only when those constants are set precisely as we observe them. The fine-tuning is an illusion created by our inability to perceive the complex, unified equation that governs all 25 parameters simultaneously. The universe is not a mistake. It is a single, beautiful mathematical statement. Its structure is not random, but mandatory, the required outcome of a cosmic arithmetic that is far more complex and far more restrictive than we currently realize. Our surprise at the fine-tuning is merely a measure of our current distance from the final, simple truth. The cosmos is patient, waiting for us to find the elegant equation that demonstrates its inevitability. The challenge to the idea of the universe as a mistake is also found in the realm of quantum mechanics and the subtle constraints it imposes on the stability of matter. The very ability of the electron to remain in orbit around the nucleus and the subsequent stability of chemical bonds is a delicate balance of the quantum rules and the electromagnetic force. The existence of stable atoms is, in itself, a profound fine-tuning of the laws of physics. According to classical physics, an electron orbiting a nucleus should continuously radiate energy and spiral into the nucleus almost instantly. The atom would collapse in a fraction of a second. This does not happen because the universe is governed by quantum mechanics, which imposes a minimum energy level on the electron's orbit, preventing it from spiraling inward. This minimum energy level forces the electron to exist in quantized, stable shells. The fine-tuning lies in the relationship between the size of the atom and the wavelength of light. The sizes of atoms, determined by the quantum mechanical rules, are incredibly small, but their stability is directly related to the mass of the electron and the strength of the electromagnetic force. If the electron mass was significantly smaller, atoms would be much larger and more fragile, potentially disrupting the formation of stable molecules. If the electron mass was significantly larger, atoms would be compressed, altering the nature of chemical bonds beyond recognition, making complex organic molecules impossible. Furthermore, the exclusion principle, a fundamental rule of quantum mechanics, is a life-permitting constraint. This principle states that no two electrons can occupy the exact same quantum state within an atom. This rule is what dictates the shell structure of the atom, ensuring that electrons fill orbitals in predictable, stable patterns. The exclusion principle is directly responsible for the entire periodic table of elements and the vast diversity of chemistry. Without it, all electrons would simply collapse into the lowest energy level, and all atoms would behave identically, leading to a chemically sterile, uniform cosmos. The exclusion principle, in a sense, is an anti-fine-tuning rule. It prevents the collapse of the quantum world. Its existence is a prerequisite for the kind of complex, differentiated matter that can form structures like DNA, proteins, and nervous systems. If the universe were a mistake, we would expect its laws to favour chaotic collapse, but instead, we find a mandatory rule that enforces quantum stability and chemical diversity. The subtlety of this quantum fine-tuning is also found in the uncertainty principle. This principle dictates that you cannot simultaneously know both the precise position and the precise momentum of a quantum particle. This inherent deep-seated randomness in the quantum world is essential for the structure of matter. If the uncertainty principle were slightly weaker, allowing for more certainty, the electrons would have too much certainty about their position, leading to a loss of the stability of their minimum energy orbit. The atom would again be vulnerable to collapse. The fundamental quantum jitter that prevents the collapse of the atom is a required feature of reality. The balance of the quantum world is thus a masterpiece of complementary forces. The electromagnetic force pulls the electrons in, while the quantum mechanical rules, the exclusion principle, and the uncertainty principle push them out and keep them organized. This stable equilibrium creates the chemical toolkit necessary for life. The question, is the universe a mistake, when viewed through the lens of quantum mechanics, finds a powerful rebuttal. The universe is not a mistake. It is a system whose rules are so robust that they prevent the collapse of matter, enforce chemical diversity, and ensure stability at the subatomic level. The very stability of the atoms that compose your hand is proof of a mandatory, non-random order woven into the deepest fabric of existence. The quiet precision of the quantum realm dictates that the universe had no choice but to be stable. The quiet integrity of the universe is further illuminated by the necessary existence of dark matter. This mysterious substance, which outweighs all the visible matter in the cosmos by a factor of 5 to 1, is not merely an observational puzzle, but a crucial, fine-tuned component, without which the universe would have remained a structureless failure. If the universe were a mistake, it would have failed to produce the precise amount and properties of dark matter required for its own long-term survival. We know dark matter exists solely through its gravitational influence. It does not emit, absorb, or reflect light, hence the name dark. Its presence is inferred by the speed at which stars orbit the centers of galaxies and the way light from distant objects is bent around galaxy clusters, a process known as gravitational lensing. Dark matter acts as the invisible scaffolding upon which all visible structure, galaxies, clusters, and the cosmic web is built. The fine-tuning of dark matter is twofold: its abundance and its interaction strength. Shutterstock. First, the abundance of dark matter is critical. If there were significantly less dark matter, gravity would have been too weak to pull the ordinary matter, the protons and neutrons, together quickly enough to overcome the universe's expansion. The early density fluctuations would have dissipated, and galaxies and stars would never have coalesced. The cosmos would be a mostly uniform, diffuse gas. If there were significantly more dark matter, gravity would have been too strong. Matter would have clumped together too aggressively and too early, leading to a universe dominated by small, dense structures, possibly preventing the formation of long-lived, stable stars like our Sun. The observed ratio of roughly 85% dark matter to 15% ordinary matter is the perfect numerical balance to allow for the slow, majestic emergence of galactic spirals and stable star systems. Second, the interaction strength of dark matter is equally fine-tuned. The key property that makes dark matter a successful scaffold is that it is cold, meaning its particles move slowly relative to the expansion of the universe, and non-interacting. Because it interacts only through gravity and not the electromagnetic or strong forces, dark matter particles do not clump too tightly together in the way ordinary matter does. This non-interacting nature allows dark matter to form massive, smooth halos that provide the initial stable gravitational potential wells into which ordinary matter can gently fall, condense, and form stars and planetary systems. If dark matter were hot, moving too fast, it would have smoothed out the density fluctuations, again preventing galaxy formation. If it interacted strongly with itself or with ordinary matter, it would have clumped too aggressively, disrupting the delicate process of star formation. The numerical constraint here suggests that the particle physics of dark matter, the mass and coupling constants of its hypothetical particles, had to be set within a very narrow, life-permitting range. The leading candidate for the dark matter particle, the weakly interacting massive particle, or WIMP, is theorized to have just the right mass and interaction strength to be naturally produced in the correct abundance in the early universe, a phenomenon sometimes called the WIMP miracle. If the WIMP miracle is true, the abundance of dark matter is not an arbitrary number, but a direct consequence of a precise physical mechanism that happens to be compatible with life. In the context of the question, is the universe a mistake? The necessary existence of dark matter provides a powerful counter-argument. The universe is not a mistake. It is a system that came equipped with a hidden, dominant component whose unique properties, cold and non-interacting, are essential for its own self-organization. Without the fine-tuned characteristics of dark matter, the laws of gravity would have failed to produce the large-scale structures we observe. Dark matter is the quiet, invisible requirement for complexity. Section 26 of 1,200 words. The ultimate question of whether the universe is a mistake is tied to the concept of simplicity and elegance in its governing laws. If the final truth of reality is a single, beautiful equation, then the current fine-tuning, the long list of 25 arbitrary constants, is not a random result, but a temporary sign of our own incomplete knowledge. The search for simplicity is the human intellect's strongest rebuttal to the idea of a cosmic accident. Science has historically favoured theories that reduce complexity to fundamental simplicity. Newton showed that the same law governs the falling apple and the orbiting moon. Maxwell unified electricity and magnetism into a single force. Einstein reduced gravity to the geometry of space-time. Each step was a move toward greater elegance and fewer arbitrary assumptions. The fine-tuning paradox, in contrast, suggests an ugly, ad hoc universe, one where a cosmic engineer had to manually adjust numerous independent dials to keep the machine from flying apart. This lack of elegance is what physicists find most philosophically troubling. The numerical coincidences are too ugly to be the final truth. They hint at a hidden symmetry that, once discovered, will render all the arbitrary constants inevitable. This search for elegance is central to the project of unification. The goal is to show that the four fundamental forces, gravity, electromagnetism, the weak and the strong forces, are not separate entities, but are different manifestations of a single, unified force that only appears distinct at the low energies of our present-day universe. The Standard Model has already achieved the electroweak unification, showing that the electromagnetic force and the weak nuclear force were one and the same at high energies, only splitting apart as the universe cooled. This unification successfully reduced several seemingly independent constants into a single framework, eliminating some of the fine-tuning problems in the particle sector. The next step is the Grand Unified Theory, or GUT, which seeks to unify the electroweak force with the strong nuclear force. If a successful GUT is found, it would naturally explain the relationships between the strengths of these three forces, reducing the number of free parameters and potentially solving the baryogenesis problem, the origin of the matter-antimatter asymmetry, through principles of symmetry. This would demonstrate that the precise numerical settings of the nuclear forces are not accidental, but are dictated by the deep structure of the ultimate law. The final goal is the theory of everything, which would incorporate gravity into the unified framework, often involving concepts like string theory or loop quantum gravity. The hope is that this final theory, by integrating gravity and quantum mechanics, will be so mathematically constrained that it has only one unique self-consistent solution. This single solution would then automatically yield the precise values for all the fundamental constants, including the electron mass and the cosmological constant that we observe to be life-permitting. If the universe is a product of this unique, elegant mathematical truth, then the fine-tuning is simply a lack of perspective. We are like musicians trying to understand a complex concerto by analysing the length of each string independently, rather than seeing the single, mandatory architecture of the entire instrument. The universe is not a mistake, it is an inevitable equation. The fact that our current understanding requires us to invoke a mistake or luck is merely a measure of the distance between our current, incomplete physics and the final, simple truth. The beauty and structural integrity of the cosmos is the strongest philosophical evidence that a single, unified, mandatory law exists, one that leaves no room for randomness or accident, and whose necessity is our only true guarantor of existence. The most compelling proof that the universe is not a mistake is found in its successful longevity. If the universe were a chaotic mistake, it would have either collapsed instantly or dispersed too quickly to sustain complex processes. The fact that the cosmos has endured for billions of years, achieving the perfect age for complexity, is a tribute to the fine-tuning of its dynamic properties. This longevity is not just about the slow pace of expansion, it is about the balance between expansion and structure formation. For a universe to be life-permitting, it must satisfy two competing constraints. First, it must expand fast enough to avoid an immediate gravitational collapse into a big crunch, and second, it must expand slowly enough to allow gravity to pull matter together into the dense clumps, stars and galaxies that are essential for creating heavy elements. The expansion rate of the universe is governed by the total energy density of the cosmos, including matter, radiation, and critically, dark energy. If the energy density had been slightly higher, the attractive force of gravity would have caused the universe to peak in expansion and immediately begin contracting, resulting in a short-lived, sterile existence. If the energy density had been slightly lower, the outward force of expansion would have overwhelmed gravity, and all matter would have dissipated without ever forming cohesive structures. The observed age of the universe, approximately 13.8 billion years, places it squarely in the window of stellar longevity. This age is not accidental. It is a direct consequence of the initial energy density being set to the perfect, critical value that allows for long-term expansion while permitting local gravitational collapse. The universe is walking the tightrope between collapse and dissolution, allowing its constituents time to evolve. The fine-tuning of this dynamic history is further highlighted by the lifespan of stars. As we have noted, stars are the universe's element factories. They must live long enough to fuse hydrogen into helium, then helium into carbon and oxygen, and finally explode as supernovae to scatter these elements into space, where they can form rocky planets and life. This requires star lifespans of billions of years. This stellar longevity is, in turn, governed by the strength of the gravitational constant and the rate of nuclear fusion, which is controlled by the weak nuclear force. The required ratio between these two forces is a non-trivial coincidence, necessary to ensure that stars burn gently for long periods rather than exploding or fading instantly. The universe is life-permitting because its history is marked by stage transitions. The initial radiation-dominated era gave way to the matter-dominated era, which allowed for structure formation, and then eventually, about 6 billion years ago, the dark energy-dominated era, which drives the current accelerated expansion. The timing of these transitions is a dynamic form of fine-tuning. If the dark energy dominance had begun earlier, galactic formation would have been suppressed. The universe waited until the necessary heavy elements were created and organized into stable planetary systems before it accelerated its overall expansion. The universe is not a mistake. It is a successful thermodynamic system that maximized its potential for complexity. Its longevity is proof of a mandated, controlled history. The laws of nature did not merely allow time to pass, they ensured that a sufficient amount of time, measured in billions of years, was available for the slow, quiet miracle of evolution to occur. This enduring, sustained existence is the strongest argument that the cosmos is an inevitable, necessary entity. The question of whether the universe is a mistake is deeply connected to the concept of dimensionality beyond the three spatial dimensions we observe. If the fundamental theories of physics, such as string theory, are correct, the universe exists in 10 or 11 dimensions, with the extra dimensions being curled up and hidden from our perception. The fine-tuning paradox is then reframed as a problem of geometrical stability. Our observable three spatial dimensions are life-permitting because they allow for stable planetary orbits and stable atomic structure, as we have discussed. The critical stability of our universe suggests that the existence of these three large, non-compactified dimensions is not an accident, but a necessary outcome of the ultimate physical law. The paradox for string theory lies in the mechanism of compactification. The theory has an immense landscape of possible stable configurations, estimated at 10 to the power of 500, each corresponding to a different way the extra 7 or 8 dimensions can be curled up. Each configuration would produce a unique set of fundamental constants for the resulting large dimensions, including the electron mass and the strength of the forces. The fact that our large dimensions have precisely the laws required for stability implies a drastic fine-tuning of the geometry of the unseen tiny dimensions. If the universe is a singular, unique entity governed by a deeper law, then that law must contain a mechanism that mandates the dynamic stabilization of three spatial dimensions and one time dimension. This mechanism would explain why the extra dimensions are so small and why their geometry generates constants that are life-permitting. The fine-tuning is then resolved by the sheer geometrical elegance of the unified theory. However, in the context of the multiverse, the dimensionality problem becomes another statistical filter. The 10 to the power of 500 possible configurations in the string theory landscape are all realized in different pocket universes. The vast majority of these universes will be sterile because their compactification geometry resulted in unstable atoms, unstable gravity, or the wrong number of large dimensions. We simply reside in the rare, lucky configuration that yielded three stable spatial dimensions and the necessary physical constants. The philosophical implication of this geometrical fine-tuning is profound. It suggests that the boundary between particle physics and cosmology is an artificial one. The size of the electron and the strength of the strong nuclear force, seemingly properties of individual particles, are actually dictated by the collective, multidimensional geometry of space-time itself. The fine-tuning paradox is not just about numbers, it is about the structure of reality. Furthermore, the stability of our one-time dimension is also non-trivial. Time in our experience flows predictably in one direction, tied to the low entropy of the universe's beginning. If the laws of physics permitted two large time dimensions, the possibility of paradoxes and highly unstable, unpredictable motion would destroy any hope for life. The unique nature of our time dimension is a prerequisite for causality and the orderly development of complexity. The universe is not a mistake, it is a geometrical necessity. The choice of three large spatial dimensions and one time dimension is the only stable configuration that allows for the complexity we observe. This precise geometrical selection is a powerful indication that the cosmos is constrained by an underlying principle of consistency, one that mandates the structural integrity of its spacetime. Our steady investigation into the universe's integrity now moves to a concept that seems far removed from cosmic constants: the information content of reality. If the universe is not a mistake, its laws must mandate not just physical existence, but the capacity for complex information processing, the very foundation of consciousness and scientific inquiry. This is the computational fine-tuning argument. The ability for the universe to support life is essentially its ability to perform complex calculations. Biological processes, DNA replication, protein folding, neural networks are all forms of information storage and transfer. For this to occur, the underlying physics must allow for the long-term stability and high fidelity of information transfer, meaning errors must be minimized and storage must be robust. The fine-tuning of this computational capacity lies in several areas we have already explored, now viewed through the lens of information theory. First, quantum stability is essential for information storage. The stability of the atom, guaranteed by the quantum mechanical exclusion principle and the fine-tuned electromagnetic force, ensures that matter does not collapse. This stability allows atoms to form into molecules, which can then act as complex, long-lived storage units, such as the double helix of DNA. If the atom were unstable, information would be erased instantly, making life impossible. The universe, therefore, is fine-tuned to be an excellent, stable information repository. Second, the chemical complexity, enabled by the laws of physics, must allow for the formation of intricate, non-repeating structures. This is where the perfect alignment of the carbon resonance is crucial. Carbon's unique ability to form four stable bonds with itself and other elements is the basis for chain, ring, and branched structures, providing the enormous combinatorial space necessary to encode the vast amount of information required for biology. If the nuclear forces had not permitted the efficient creation of carbon, or if the electron mass had been slightly different, limiting bonding versatility, the computational capacity of the universe would be drastically reduced to simple, linear, uninteresting molecules. Third, low entropy is the prerequisite for processing information. The overall ordered state of the early universe allows energy gradients to exist, such as the heat difference between the sun and the cold of space. These gradients provide the available energy, or free energy, necessary to perform work like powering a cell or a computer. Without a difference in energy potential, no computation can occur. The universe's fine-tuned low-entropy start is, in effect, the fine-tuning of computational power over billions of years, ensuring that the necessary energy is available to drive complexity. Fourth, the speed of light sets the ultimate limit on how fast information can travel, and, therefore, on the size of any coherent information processing system. The speed of light is not infinitely fast. It is a fixed, non-negotiable constant. This fixed speed ensures causality. That cause precedes effect, which is essential for any logical system. If the speed of light were much slower, the size of a single brain, or even a single galaxy, would be too large to process information coherently across its expanse. If the speed of light were too fast, the dynamics of star formation might be altered, disrupting the slow accretion necessary for stability. The speed of light is the perfectly set clock speed for the cosmic computer. The universe is not a mistake, it is a mandatory information processor. The cumulative fine-tuning of its constants demonstrates that the laws of physics are structured to facilitate the emergence of complexity, stability, and ultimately, consciousness. The ability of the universe to recognize and compute its own laws. This is the strong anthropic principle in its most technical form. The laws must be such that they allow for the emergence of the observers who decode the information. The universe has a deep, underlying mandate for organization and complexity. The most profound philosophical challenge to the fine-tuning argument and the assertion that the universe is a mistake comes from the potential existence of a single, non-random, unique theory of everything. This belief holds that the final, unified set of physical laws will be so mathematically constrained that it leaves no room for randomness, arbitrary constants, or multiple possibilities. The fine-tuning is simply a lack of perspective. If such a mandatory law exists, it must be so powerful and self-consistent that all of the 25 arbitrary constants we currently measure, from the electron mass to the dark energy density, are mathematically derived from the single core equation. In this view, the universe is not lucky, it is logically inevitable. The hope for this inevitability rests on the concept of symmetry and completeness. A unified theory would show that the laws of nature are symmetrical, meaning they remain the same regardless of observer, location, or time. The current fine-tuning, the immense numerical gulfs between forces and particle masses, is viewed as a broken symmetry at low energies that will be restored at the ultra-high energy scale of the unified theory. For example, the hierarchy problem, the vast difference between the gravitational scale and the Higgs scale, suggests a broken symmetry. Theories like supersymmetry attempt to restore this symmetry by postulating that every particle has a partner. If successful, supersymmetry eliminates the need for the miraculous 1 part in 10 to the power of 32 cancellation that keeps the Higgs light. The fine-tuning is gone, replaced by a symmetrical necessity. Furthermore, a true theory of everything must be complete, meaning it must unify the seemingly contradictory worlds of general relativity and quantum mechanics. The current tension between the smooth geometry of space-time and the discrete, uncertain nature of the quantum world is where the fine-tuning paradox thrives. If a theory, like loop quantum gravity, is correct, space itself is not smooth, but is composed of tiny, discrete loops, or pixels. This quantization of space-time might naturally impose constraints on the size and strength of the forces, ultimately dictating the fundamental constants. The philosophical implication of a unique theory is that it elevates the universe from a random accident to a metaphysical necessity. If the ultimate law is a self-consistent truth, then any universe governed by that law must possess the life-permitting properties we observe. The fine-tuning paradox is dissolved by the realization that the probability space for constants is not continuous and vast, it is zero. There is only one choice. However, the challenge remains that such a unique self-consistent theory has been notoriously difficult to find. String theory, the leading candidate, has the immense problem of the string theory landscape. The 10 to the power of 500 possible self-consistent solutions. This vast landscape suggests that even the ultimate theory might permit an enormous range of possible universes, forcing the argument back into the realm of the multiverse. If the string theory landscape is correct, the fine-tuning paradox is only solved by accepting the multiverse as an external constraint. Our universe is not unique. It is simply the life-friendly solution chosen from a geometrical landscape of possibilities. The search for the ultimate truth becomes a search for the law that dictates which corner of the landscape we reside in. The universe is not a mistake. It is a profound, unique statement. The very act of seeking the unifying law is a quiet, intellectual commitment to the belief that the cosmos is fundamentally comprehensible and non-arbitrary. The persistence of the fine-tuning paradox is simply the universe's way of telling us that the final, most elegant answer is still just beyond our current reach. The hope is that the necessity of elegance will eventually triumph over the appearance of accident. The most unsettling argument against the non-accidental nature of the universe is the potential existence of observer-created reality, a philosophical extreme where the universe's fine-tuning is not a precondition for our existence, but a consequence of it. This idea suggests that the question, is the universe a mistake, though, is rendered meaningless because the act of observation itself collapses the enormous possibilities into the single, life-permitting reality we inhabit. This philosophical viewpoint is inspired by the deepest, most counterintuitive aspects of quantum mechanics, particularly the problem of measurement. In the quantum realm, particles exist in a superposition of multiple states until they are measured, at which point the wave function collapses into a single, definite outcome. This suggests that the observer plays a non-trivial role in defining reality. The multiverse concept, particularly the many worlds interpretation of quantum mechanics, takes this idea to its extreme. This interpretation suggests that every time a quantum measurement is made, the universe splits into a multitude of parallel universes, one for every possible outcome. If the physical constants are seen as the ultimate quantum parameters, existing in a superposition of all possible values, then the moment a conscious observer measures them, the universe collapses into the single, precise configuration that includes the existence of the observer. The fine-tuning paradox in this light is explained not by external luck, but by internal selection. The entire string theory landscape of 10 to the power of 500 possible universes is constantly being realized, but we, as observers, can only ever perceive the slice of reality where the collapse yielded the life-permitting constants. The universe is not a mistake. It is a self-selected reality, determined retroactively by the existence of consciousness. This perspective bypasses the need for both an elegant deeper law and a randomly lucky Big Bang. The laws themselves are inherently non-unique and arbitrary, but the presence of the observer filters the infinity into a necessary singularity. The incredible precision of the gravitational constant or the carbon resonance is simply the required condition for the measurement to take place. However, this argument faces severe philosophical and scientific criticisms. It raises the issue of when and what constitutes an observer capable of collapsing the wave function. Is it a bacterium, a brain, or merely a piece of inanimate measuring equipment? If the physical constants themselves are subject to observer collapse, it implies that the laws of physics were unstable until consciousness arose, a concept that fundamentally challenges the objectivity of science. Furthermore, the idea of observer-created reality struggles with the problem of simplicity. If the universe could have been anything, why did the observed reality collapse into one that is so precisely governed by elegant, simple mathematical rules? Why not a chaotic, unpredictable reality? The fact that the observed universe adheres to simple, powerful, and invariant laws suggests that its structure is mandatory, not optional or observer-dependent. The elegance of the laws seems to precede the existence of the observer. The quiet truth is that the finest numerical constants of nature, the strength of gravity, and the mass of the electron, were fixed long before the first conscious life evolved. They were fixed during the recombination era and the formation of the first stars, billions of years before Earth existed. If these constants were truly observer-dependent, the existence of the cosmic microwave background, a relic of a time before life, should not adhere to such precise, fine-tuned thermal stability. The universe is not a mistake. It is a system with objective constraints. The fine-tuning paradox is a challenge to our understanding of those constraints, not a challenge to the objectivity of reality. The laws of nature are the rigid framework that allows for the emergence of consciousness, not a fluid tapestry woven by it. Our investigation of the universe's non-accidental status must address the phenomenon of causality and its intimate relationship with the fixed speed of light. If the universe is not a mistake, its laws must mandate a predictable, non-paradoxical flow of time, which requires the speed of light to be an absolute, non-negotiable constant. The speed of light in a vacuum is the ultimate fine-tuned constant. It is the fixed cosmic speed limit that governs all information, transfer, interaction, and causality in the universe. Relativity tells us that nothing can travel faster than light, ensuring that cause always precedes effect. This is the causal structure of space-time, a required framework for any logical, time-evolving system, including life. The fine-tuning of the speed of light is related to its role in the electromagnetic force and the masses of fundamental particles. If the speed of light were significantly slower, the dynamics of star formation would be disrupted, and the long-range forces that bind matter would operate differently, potentially preventing stability. Furthermore, as we noted, a slower speed of light would constrain the size of any coherent information processing system, making anything larger than a microbe unstable. If the speed of light were infinitely fast, the entire concept of a local reality would disintegrate. Every event in the universe would be simultaneous with every other event, removing the sequential flow of time and causality. The concept of an event would become globally instantaneous, preventing the gradual step-by-step evolution required for complexity. An infinitely fast speed of light would create a sterile, non-evolving cosmos without structure or sequence. The paradox here is that the speed of light is an arbitrary constant within our current physics. Why is it precisely the value it is? The deeper law perspective argues that the speed of light is not independent, but is determined by the properties of the vacuum itself, possibly linked to the fine structure constant that governs the strength of electromagnetism. If the fine structure constant is constrained by the unified theory, the speed of light is constrained as well. The speed of light also provides a crucial check on the fine-tuning of the early universe. The horizon problem in cosmology asks why distant regions of the universe, which were too far apart to have ever exchanged light and achieved thermal equilibrium, according to the standard Big Bang model, still possess the exact same temperature today as observed in the cosmic microwave background. The solution is cosmic inflation. The theory posits that the universe expanded exponentially in the first tiny fraction of a second, meaning that distant regions were once close enough to reach thermal equilibrium before inflation stretched them far apart. This successful explanation of the horizon problem relies on the speed of light being fixed and on the precise rate of the inflationary expansion. If the speed of light were different, the inflationary solution to the horizon problem would fail. The universe would be a highly inhomogeneous, chaotic, and non-uniform mistake. The universe is not a mistake. It is a system that mandates causality. The fixed speed of light is the most rigid, non-negotiable law of our reality, essential for the existence of sequential time, stable structure, and the very possibility of local observation. This required speed limit is the universe's quiet declaration of its own integrity, a law that enforces order and prevents the philosophical chaos of a non-causal reality. The precise value of this cosmic speed limit is the ultimate prerequisite for the sequential process of life. The quiet integrity of the universe is further tested by the question of randomness versus determinism. If the universe is a mistake, it implies a fundamental role for chaos and chance in its deepest laws. If it is inevitable, it implies a rigid determinism, where every event, including our own thoughts, is predetermined by the initial conditions. The fine-tuning paradox suggests that the universe has chosen a required narrow path between these two extremes. A universe that is purely deterministic would be governed by classical laws that precisely predict every future state from the initial conditions. This deterministic world, however, often struggles with the emergence of true novelty, complex structures, and, critically, consciousness, which seems to require a degree of freedom and unpredictable interaction. A universe that is purely random would be governed by laws that are so weak they permit total chaos. In such a world, the fine-tuned constants would quickly drift, and the complex structures required for life would fail to maintain their stability over long periods. A universe of pure chance is hostile to the long, slow work of evolution. The fine-tuning paradox demonstrates that our universe resides in a mandated balance, exhibiting local chaos within a global determinism. The laws of physics are rigid enough to ensure the long-term stability of the constants, the formation of stars, and the reliable cycle of elements, providing the deterministic framework for life. However, within this framework, the essential laws of quantum mechanics introduce a necessary local randomness. The quantum world, governed by the uncertainty principle and the probabilistic nature of particle interactions, is fundamentally non-deterministic. This quantum randomness is not a flaw, it is essential for the complexity of the universe. For instance, the spontaneous decay of an atom, governed by quantum probability, is what drives the heat production in Earth's core, which is necessary for plate tectonics and the long-term carbon cycle that stabilizes the planet's climate. Without this necessary quantum chaos, the Earth would be a geologically dead, sterile world. Furthermore, the stability of the Higgs field, which determines particle mass, is itself a fine-tuned balance between symmetry and randomness. The Higgs mechanism, which gives mass to particles, occurs when a symmetry breaks as the universe cools. This process involves a necessary element of randomness in how the field settled to its lowest energy state, ensuring that the final particles have the precise, life-permitting masses. The fine-tuning is that the laws are rigid enough to enforce the symmetry breaking, but loose enough to permit the low, life-friendly Higgs mass. The universe is not a mistake. It is a system that has chosen a required level of randomness. This required randomness, or quantum uncertainty, is just enough to facilitate the novelty, complexity, and evolutionary potential required for life to emerge, but not so much that it destroys the deterministic framework of stable atoms and stars. The question, is the universe a mistake, is resolved by the realization that its laws mandate a synthesis, a stable, deterministic environment large enough to harbour life, built upon the unpredictable, probabilistic foundation of the quantum realm. This precise, life-permitting blend of order and chaos is the ultimate proof of a non-accidental design. Our exploration of the fine-tuning paradox must also encompass the subtle role of consciousness itself, moving the argument from pure physics to the intersection of complexity and perception. If the universe is not a mistake, its fine-tuned laws must have a deep, necessary link to the potential for self-awareness. The strong anthropic principle asserts that the universe must possess properties that allow life to evolve. This assertion can be interpreted as suggesting that consciousness is not merely a lucky byproduct of the fine-tuned constants, but is an inevitable goal or required outcome of the physical laws. The key fine-tuning here relates to the complexity required for a self-aware entity to emerge. Consciousness requires a massive amount of information processing, organized structures, like a brain, and long-term stability. This requires the universe to be fine-tuned not just for simple life, but for the highest degree of complexity. The necessary fine-tuning for complexity includes the ability of carbon to form long, intricate molecular chains, the perfect properties of water as a solvent and thermal buffer, and the long-term stability of the proton to ensure that complex structures do not decay instantly. All these factors are individually improbable, but their simultaneous existence points to a universe that is maximally optimized for the generation of complexity. Furthermore, the universe is fine-tuned for non-locality in its interactions. The forces of gravity and electromagnetism, which are required to form stars, planets, and even the chemical bonds of a brain, are long-range forces. They follow the inverse square law and extend their influence across vast distances. If these forces were purely local, decaying instantly over small distances, no large-scale structure, no stars, no planets, no brains could form. The long-range nature of these forces is a fine-tuned prerequisite for large-scale organization and the complex network required for consciousness. This fine-tuning suggests that the universe has a deep underlying mandate for self-organization. The laws of physics are structured to spontaneously generate complexity from simple initial conditions, moving from pure energy to matter, to atoms, to molecules, to self-replicating systems, and finally, to conscious entities capable of understanding the laws that created them. The universe is not a mistake, it is an algorithm for complexity. The fine-tuned constants are simply the required settings for this algorithm to run its course successfully. The gravitational constant is set to create the long-lived stars that create the carbon. The nuclear forces are set to ensure that carbon is created and is chemically versatile. The ultimate product is an observer, a mind that can reflect on the necessity of its own existence. The question, is the universe a mistake, therefore finds its most profound answer in the existence of the questioner. If the universe were a mistake, it would have failed to generate the necessary complexity to host consciousness. The fact that we are here, capable of analyzing the physical laws, is the universe's ultimate proof of concept, a demonstration that its structure is not random but mandatory for the emergence of self-awareness. The universe is fine-tuned to be conscious of itself. Our quiet examination of cosmic necessity must include the question of tuning by selection, an idea that seeks to find a natural, non-random filter that resolves the fine-tuning paradox without resorting to an infinite multiverse or an arbitrary deeper law. If the universe is not a mistake, it may be because its laws are merely the most stable, most enduring form of existence possible. This argument suggests that the universe has undergone a process akin to cosmological natural selection, as proposed by physicist Lee Smolin. This hypothesis attempts to provide an internal, non-anthropocentric explanation for the fine-tuning. It proposes that the laws of physics are not fixed, but evolve over cosmic time. The core mechanism of this selection is the black hole bounce. Smolin posits that every time a black hole forms, the singularity at its core acts as a rebirth event, causing a new, infant universe to bounce out of the space-time fabric. This new universe inherits the fundamental constants of its parent universe, but with a slight random mutation. In this scenario, universes that are more fertile, that is, universes that produce more black holes, are more successful at reproduction and dominate the vast ensemble over infinite time. The selection pressure is enormous. Any universe with constants that are not fine-tuned for efficient star formation, long stellar lifespans, and the creation of heavy elements, would fail to produce many massive stars, and thus fail to produce many black holes. These sterile universes would quickly die out, leaving few offspring. The beauty of this concept is that the conditions for maximal black hole production are precisely the conditions required for life. First, a precise gravitational constant is required to allow stars to form and grow massive enough to collapse into black holes. Second, the correct nuclear forces are necessary to allow the star to burn stably for a time, then enrich its core with the iron necessary for the final, sudden collapse. Third, the existence of 3 spatial dimensions is required for gravity to operate effectively across long distances to pull mass together. Crucially, the conditions that favour high black hole fertility also happen to favour the emergence of life. The stable, long-lived stars and the abundant heavy elements needed for life are also the necessary ingredients for black hole formation. The fine-tuning is not for us, the observers, but for maximum fecundity. We are merely the bystanders in a universe optimized for reproduction. This hypothesis eliminates the need for an arbitrary external selection, the multiverse, and an impossible initial probability, the single universe model. The universe is not a mistake. It is a highly successful competitor in an eternal, evolving cosmic ecosystem. The laws we observe are not lucky. They are simply the laws that have been selected for stability and efficiency over the longest period of time. However, the hypothesis of cosmological natural selection is extremely difficult to test. Its predictions rely on observing deviations from the standard physical laws, and for now, the observed universe adheres perfectly to the non-evolving standard model. Furthermore, critics argue that the assumption that universes reproduce through black holes is currently untestable and purely speculative. Despite the difficulties, the concept provides a powerful, naturalistic answer to the fine-tuning paradox. It suggests that the immense numerical precision of our constants is not a miracle, but an evolutionary necessity. The universe is the ultimate survivor, a system whose very laws have been honed and sharpened by billions of years of cosmic competition. The non-randomness of the cosmos is a consequence of its ability to self-propagate, ensuring that only the most life-permitting, or rather, the most black hole-producing, configurations endure. Section 36 of 40, 1,200 words. The culmination of the fine-tuning argument is found in the ultimate question of why these laws. The paradox asks not just why the constants are set correctly, but why the form of the physical laws themselves, the inverse square law for gravity, the precise relationship between energy and momentum, the structure of quantum mechanics, are so perfect for complexity. This suggests a metaphysical constraint on the universe's possibility space. If the universe were a mistake, one would expect the laws to be messy, arbitrary, and riddled with inconsistencies. Instead, we observe laws that are stunningly simple, mathematical, and invariant. The laws of physics are expressed in elegant, differential equations that hold true everywhere in the cosmos, regardless of time or location. The inverse square law, for instance, which governs both gravity and electromagnetism, dictates that the force diminishes with the square of the distance. As we have discussed, this is the only force law compatible with three stable spatial dimensions and with the principle of energy conservation. If the force diminished with the cube of the distance, planetary orbits would be unstable. If it diminished with the distance itself, atoms would collapse. The form of the law itself is fine-tuned to ensure stability. This suggests that the universe is not just fine-tuned numerically, but formally. The very structure of the laws of physics is constrained by the required stability and self-consistency of the cosmos. The universe is not merely lucky, it is structurally mandatory. This idea leads to the concept of mathematical inevitability. Some philosophers and physicists, subscribing to a modern form of Platonism, argue that mathematical entities, such as the laws of physics, exist independently of the physical universe, and that the universe is merely a physical manifestation of the one, unique, self-consistent mathematical reality. If this is true, the fine-tuning paradox dissolves entirely. The constants are set correctly because the laws themselves are unique and non-optional. The universe must have the form that it does, because no other form is mathematically possible. This perspective views the fine-tuning as a powerful clue that the human mind is close to discovering the ultimate simple law that underpins everything. The fine-tuning problems, the massive gap between gravity and the other forces, the precise cancellation of the vacuum energy, are seen as guideposts directing us toward a principle of unity and elegance. The universe is not a mistake, it is a mandatory consequence of mathematics. The laws are not arbitrary choices. They are the unique, non-negotiable grammar of existence. Our search for a theory of everything is therefore a search for the unique mathematical axiom from which the entire structure of the physical universe flows. In the final quiet contemplation of our existence, the fine-tuning paradox is transformed from a question of statistical odds into a search for necessary truth. The universe, with its precise constants, its stable atoms, its long-lived stars, and its perfectly balanced expansion, appears to be an optimized system, constrained by a deep, unwavering mandate for structure and complexity. The only way the universe could be a mistake is if the mathematical reality itself permitted flaws. Given the elegance and precision we observe, the evidence suggests otherwise. The cosmos is an objective, inevitable fact. Our penultimate turn in this quiet inquiry focuses on the argument of minimum complexity. If the universe is not a mistake, its laws must be fine-tuned not merely for existence, but for the minimum necessary conditions required for complexity to emerge and evolve. This suggests a cosmos that is elegantly efficient, not wasteful or random. The core of this argument is that for any form of conscious life to arise, the physical environment must satisfy a hierarchical list of required conditions. The fine-tuning we observe is precisely for these foundational requirements, and nothing more, suggesting a form of cosmic efficiency rather than arbitrary chance. First, the requirement for long-term stability is met by the fine-tuning of the expansion rate, the cosmological constant, and the geometry, the flatness of space. This ensures that the universe will not collapse or dissipate before billions of years have passed. This is the temporal fine-tuning, setting the cosmic clock to run long enough. Second, the requirement for atomic stability is met by the fine-tuning of the electromagnetic force, the electron mass, and the proton-neutron mass difference. This ensures that matter can exist as stable atoms and that chemistry is possible. This is the chemical fine-tuning, setting the toolkit for complexity. Third, the requirement for element synthesis is met by the exquisite fine-tuning of the strong nuclear force to produce the carbon resonance. Without this, the entire chain of life-supporting elements would break. This is the nuclear fine-tuning, setting the factory for the required ingredients. The argument for minimum complexity suggests that the laws of physics are only fine-tuned to the level required for the possibility of life, and not beyond. If the universe were truly arbitrary, or if it were created by an omnipotent, non-constrained designer, one might expect to see constants set to values that are too good for mere life. For example, if the fine-tuning were for perfect stability, the laws might mandate that all planets remain perpetually unchanged, preventing the geological activity and evolutionary change that is necessary for complex life. Instead, we observe a universe that is poised on the very edge of chaos. The life-permitting zone is often narrow, suggesting a minimal set of constraints rather than an infinitely wide margin of safety. This minimal, efficient tuning suggests that the cosmos is structurally constrained to be this way, rather than arbitrarily chosen. Consider the role of chaos and order. Life requires order, the stable, predictable laws of physics, the stable orbits, the stable atoms. But life also requires chaos, the quantum uncertainty that prevents atomic collapse, the geological turbulence that drives plate tectonics, and the cosmic disorder of supernovae explosions that seed the universe with heavy elements. The universe is fine-tuned to allow for a small, life-permitting degree of disorder within a global framework of order. If the initial conditions had been set to yield a universe of perfect total order, all structure would have remained static, preventing the energy flow and chemical reactions necessary for life. If the universe is not a mistake, it is because its laws are set to the minimal point of stability, maximizing the potential for dynamic, evolutionary change. This concept of minimum complexity strengthens the case for a deeper law. A final, elegant theory of everything would naturally be minimal, deriving the largest possible structure from the fewest possible initial assumptions. The fine-tuning we see is simply the reflection of this required minimal elegance projected onto our low-energy, four-dimensional reality. The universe is not over-designed. It is designed with the highest degree of mathematical economy. The universe is not a mistake. It is a masterpiece of efficiency. Its laws are set precisely to the minimum necessary requirements to ensure that the slow, quiet process of cosmic evolution, from hydrogen to humanity, can unfold successfully over billions of years. Our final scientific contemplation returns to the concept of testability. If the universe is not a mistake, but the logical consequence of a unique non-random law, then the search for that law should be observable, not merely philosophical. The ultimate test of the fine-tuning paradox lies in the next generation of experiments searching for physics beyond the standard model. The fine-tuning paradox is essentially a set of unsolved problems within our current physics, each of which points to an underlying inconsistency. If the standard model were the complete final law, the fine-tuning would be arbitrary. The fact that the universe exists requires us to look for the physics that resolves these inconsistencies. The most critical test is the search for supersymmetry at particle accelerators. The hierarchy problem, the miraculous cancellation of 1 part in 10 to the power of 32 that keeps the Higgs boson light, is the most urgent fine-tuning paradox in particle physics. If supersymmetry is discovered, the puzzle is solved. The universe is not lucky, it is symmetrical. The existence of superpartner particles would provide the natural quantum cancellation required to stabilize the Higgs mass, eliminating the appearance of accident. The absence of superpartners, however, forces the paradox back onto the table, suggesting either a much more bizarre fine-tuning mechanism or strengthening the multiverse argument. A second critical test lies in the search for dark matter particles. The required abundance and non-interacting nature of dark matter are key fine-tuning constraints for galactic stability. If dark matter is identified as the weakly interacting massive particle, or WIMP, it would confirm the WIMP miracle, showing that the dark matter abundance is a natural consequence of the weak nuclear force and the particle's mass. This would eliminate another arbitrary number and suggest a deep, life-permitting link between the weak force and cosmic structure. A third test is the search for neutrino mass generation. The incredibly small, fine-tuned mass of the neutrino is essential for galaxy formation. The hypothesized seesaw mechanism suggests that this minuscule mass is a consequence of an incredibly massive, sterile neutrino in a hidden sector of the universe. If experiments confirm this mechanism, the smallness of the neutrino mass is explained not by luck, but by a mandatory inverse relationship with a hidden massive scale of physics. This is the quiet promise of the deeper law. If, over the next 2 decades, these experiments confirm a suite of new physical laws, supersymmetry, the WIMP, and the seesaw mechanism, the vast majority of the arbitrary fine-tuned constants will have been replaced by a system of interlocking, non-optional principles. The entire numerical argument for the universe being a mistake will be undermined. The universe is not a mistake. It is a testable hypothesis of inevitability. The persistence of the fine-tuning paradox is merely a measurement of the small gap between our current knowledge and the final unified truth. The scientific method's ability to identify and relentlessly pursue these numerical inconsistencies is the most powerful argument against the idea of cosmic accident. The universe is waiting for us to catch up to its own perfect underlying logic. Our final, quiet contemplation of the fine-tuning paradox returns to the philosophical core of the question. Is the universe a mistake because it is improbable? Or is it inevitable because it is beautiful? The universe's overwhelming aesthetic elegance is, for many, the final, non-numerical argument against its accidental status. The history of physics demonstrates a profound link between mathematical beauty and physical truth. The most successful theories, Newton's laws, Maxwell's equations, Einstein's general relativity, are characterized not just by their accuracy, but by their stunning simplicity, symmetry, and elegance. These theories reduce a seemingly chaotic complexity to a few core, beautiful principles. General relativity, for instance, expresses the enormous complexity of gravity through the elegant geometry of space-time curvature. The physical universe, in its deep structure, seems to adhere to an aesthetic mandate for conciseness. The fine-tuning paradox, however, suggests a universe that is aesthetically ugly. The necessity of setting 25 independent, seemingly random constants to values of improbable precision feels arbitrary, clumsy, and inelegant. A universe that requires a numerical kludge to avoid instant collapse lacks the deep, inherent simplicity expected of a final reality. This aesthetic dissonance is the strongest philosophical drive to search for a deeper law. The belief is that the final theory of everything will be so elegant, so symmetrical, that it will automatically resolve the fine-tuning paradox by showing that the current constants are not arbitrary choices, but mandatory consequences of the theory's required mathematical self-consistency. If the universe were a mistake, we would expect the final laws to reflect that randomness, exhibiting complexity and arbitrary numerical relationships. The fact that physicists relentlessly pursue symmetry and simplicity suggests a pre-scientific faith in the universe's underlying non-accidental order. Furthermore, the beauty of the cosmic web itself, the vast filamentary structure of galaxies clustered around immense voids, is a consequence of the fine-tuned initial density fluctuations. If the initial conditions had been too chaotic, the universe would be an amorphous mess. If they had been too uniform, it would be featureless. The observed structure, a beautiful, predictable, complex web that is both random and ordered, is the physical manifestation of the precise balance between gravity and expansion. This resulting beauty is not merely subjective, it is the visual proof that the dynamic history of the cosmos unfolded with exquisite control. The universe is not a mistake, it is an aesthetic imperative. Its deep structure dictates elegance, and its evolutionary history yields ordered complexity. The pursuit of the solution to the fine-tuning paradox is, at its heart, the pursuit of cosmic beauty, the belief that the final, most complete description of reality will not be a random list of numbers, but a singular, elegant truth that leaves no room for accident. We arrive now at the quiet culmination of our journey. The question, is the universe a mistake, has been exposed as a paradox, born not from chaos, but from the immense precision of existence itself. The fine-tuning is either an improbable accident that required 120 orders of magnitude of luck, or a mandatory consequence of an underlying physical and mathematical necessity. The evidence for the non-accidental status of the universe is found in the quiet, interlocking constraints. The strength of gravity is perfectly balanced with the weak nuclear force to ensure stellar longevity. The strong nuclear force is precisely set against the electromagnetic force to enable the efficient creation of carbon, and the dark energy density is minuscule enough to allow 8 billion years of stable structure formation before accelerating expansion takes over. The universe is a nested hierarchy of perfect numerical coincidences. The three possible responses remain the quiet answers to the paradox. First, pure chance, the mistake. This asserts that the universe is a lucky singular fluke. The fine-tuned constants were drawn arbitrarily, and we are merely the survivors of an event that was almost certainly going to fail. This is scientifically unsatisfying because it halts the search for a deeper explanation and accepts the numerical ugliness of the required precision. Second, the multiverse, the statistical error. This asserts that the universe is not unique, but one of an infinite number of bubbles, each with random constants. Our fine-tuned existence is guaranteed by the sheer number of tries. This is scientifically challenging because the parallel universes are currently untestable. It solves the improbability by postulating infinite non-existence. Third, the deeper law, the inevitability. This asserts that the fine-tuning is an illusion. The fundamental constants are not independent dials, but are mandatory outputs of a single, unique, self-consistent theory of everything. This is the most demanding hypothesis, requiring the discovery of the physics that unifies gravity and quantum mechanics and eliminates all arbitrary numbers. The persistent existence of the fine-tuning paradox is the universe's own profound declaration that our understanding is incomplete. It is a powerful, non-negotiable set of numerical constraints that forces us to seek physics beyond the standard model, to find the symmetry that resolves the hierarchy problem, the mechanism that explains the tiny neutrino mass, and the principle that dictates the near-zero value of dark energy. The universe is not a mistake, it is a mandated puzzle. Its laws are structured to be mathematically inevitable, and its history is timed to facilitate the emergence of consciousness. The question of whether it is an accident is merely a symptom of our current distance from the final, elegant, self-contained truth. The cosmos has a profound, inherent mandate for order. Let the edges of the inquiry soften now. The numerical constraints remain, as rigid and elegant as the day they were set. Whether the universe is a single, perfect mathematical necessity, or merely the most successful survivor in an infinite, evolving reality, the quiet precision of its laws is the ultimate proof of its integrity. We are not a mistake, but the logical consequence of a cosmos that required an improbable, yet perfectly executed, balance to exist. Sleep well beneath the quiet certainty of the universe's non-accidental arithmetic.